Imagine staring up at the night sky, gazing at the vast emptiness between the stars, and realizing there's something there, something massive, yet almost completely invisible. Scientists have spent decades searching for it, and most people don't even know it exists. But it's been right above us all along, hiding in plain sight. These are the Kordylewski Clouds, two giant dust clouds orbiting Earth, so faint that for most of human history, they remained undiscovered. But here's the real mystery. No one fully understands what they are, how long they've been there, or what they might mean for the future of our planet. Could they be remnants of ancient cosmic events? Could they affect space travel in ways we haven't even considered? Or, more strangely, could they be evidence of something we don't yet have the tools to comprehend? Kordylewski clouds are like ghostly shadows in space. Unlike the bright, solid moon, or the countless satellites orbiting Earth, these clouds don't shine or reflect light in a way that makes them easy to see. Instead, they blend into the darkness, made up of countless tiny dust particles, stretching across space in ways we're only beginning to understand. They sit at two specific points in space, places known as Lagrange points, where the gravitational pull of the Earth and Moon balance out, creating stable regions where objects can linger. These clouds exist at L4 and L5, two of these special points in the Earth-Moon system, and they've likely been there for a very, very long time. For years, the Kordylewski clouds remained one of those strange, almost forgotten scientific curiosities, something that was talked about in niche academic circles but wasn't widely accepted as real. But then, in 2018, modern technology caught up. A team of Hungarian astronomers used advanced polarizing filters to observe the faint light scattering off these dust clouds, finally confirming their existence beyond doubt. The Kordylewski clouds weren't just a theory anymore. They were real. But the confirmation of their existence raised even more questions. How did they form? Are they remnants of dust from the early solar system, trapped in these gravitational eddies for billions of years? Are they continuously replenished by asteroid impacts or cosmic debris? And more importantly, what impact, if any, do they have on Earth? One of the biggest mysteries surrounding the Kordylewski clouds is their stability. Theoretically, dust clouds shouldn't be able to persist in Lagrange points indefinitely. The forces of the Sun, Moon, and Earth constantly shift, and even small gravitational tugs from passing asteroids or space debris should, over time, scatter the dust away. But somehow, these clouds are still here. Scientists believe that they may not be singular, permanent structures but rather continuously reforming swarms of dust. In other words, the dust in these clouds may not be the same particles that existed centuries ago, but the overall shape and structure of the clouds persist because new dust is always moving in to replace what is lost. This raises another important question: where is all this dust coming from? Some researchers speculate that it could be material ejected from the Moon, kicked up by meteorite impacts, and slowly drifting toward the L4 and L5 points, where it gets trapped in the delicate gravitational balance. Others suggest that interplanetary dust, tiny fragments from comets and asteroids passing through the solar system, could be accumulating there over time. But there's another, more unsettling possibility. Could the Kordylewski clouds be part of a much larger, hidden system of dust rings around Earth? We already know that Earth has a faint dust ring along its orbit, created by the slow accumulation of interplanetary particles. But if the Kordylewski clouds exist, it suggests that dust can be trapped in other unexpected locations. Could there be more of these structures lurking in the shadows of space, undetected and waiting to be discovered? The implications of this go beyond just academic curiosity. If these clouds are stable enough to persist over long periods, they could pose a hidden challenge to space exploration. Imagine a future where spacecraft traveling to the Moon or beyond have to navigate through dense regions of microscopic dust that could damage sensitive instruments, erode surfaces, or even create unpredictable hazards. We already know that space dust is a serious issue. Particles moving at high speeds can cause significant damage to satellites and spacecraft. If the Kordylewski clouds are denser than we currently realize, they could represent an unseen danger that future missions need to account for. But beyond the practical concerns, there's something undeniably eerie about the idea that enormous, ghostly clouds have been orbiting Earth this whole time, unseen by the human eye. How many other things are out there, hidden just beyond our perception? The universe is full of mysteries, some so distant that we can only observe them through powerful telescopes, and others so close that we've somehow overlooked them for centuries. The Kordylewski Clouds are a reminder that space is not empty. Even in the places we assume are voids, there are still unknown structures, forces, and phenomena waiting to be understood. And perhaps the biggest question of all is, what else are we missing? If it took us until the 21st century to confirm the existence of dust clouds orbiting our own planet, what other cosmic structures are hiding in the darkness? Could similar clouds exist around other planets, forming hidden rings of dust that we've never detected? Could there be unknown forces influencing their formation, forces that don't fit into our current models of gravity and celestial mechanics? The search for answers is just beginning. The more we learn about the Kordylewski Clouds, the more we realize how little we truly understand about the space around us. They are a piece of a larger puzzle, one that could change our understanding of planetary systems, cosmic dust, and the delicate balance of forces that shape our universe. The realization that the Kordylewski Clouds are real has opened a floodgate of new questions, pushing scientists to rethink what we know about space dust and celestial mechanics. If these vast clouds of particles can persist at Lagrange points for long periods, then it suggests that these regions of space are more complex than we assumed. The Earth-Moon system is not just a two-body dance. It's a dynamic, ever-changing environment filled with hidden structures, gravitational anomalies, and possibly even other undiscovered formations. One of the most intriguing aspects of the Kordylewski Clouds is their potential role in planetary science. If Earth has these dust clouds at L4 and L5, could other planets have similar structures? Could Mars, for example, have hidden dust clouds orbiting at its own Lagrange points with its moons, Phobos and Deimos? And if so, could these clouds reveal something about the history of dust migration in our solar system? To answer these questions, scientists have begun looking at other planetary systems. If dust clouds like these can exist around Earth, then exoplanets, planets orbiting distant stars, could also have similar formations. Studying the Kordylewski Clouds could provide a template for identifying dust structures around other worlds. This is especially exciting because detecting exoplanets themselves is already difficult, let alone finding faint dust clouds orbiting them. But if we can understand how these clouds form and persist in our own cosmic backyard, we may be able to predict where to find them elsewhere in the universe. One of the key factors that makes the Kordylewski Clouds so elusive is the way they interact with light. Unlike planets or moons, which reflect sunlight clearly, these clouds scatter light in a much more subtle way, making them nearly impossible to see with the naked eye. This is why it took so long to confirm their existence. Our usual methods of astronomical observation simply weren't designed to detect something so faint and diffuse. But recent advances in imaging technology have changed the game. The Hungarian astronomers who confirmed the Kordylewski Clouds in 2018 used a technique called polarization detection, which measures the way light waves scatter when they pass through a medium. By carefully analyzing the patterns of polarized light, they were able to pick up the distinct signature of dust particles in the L4 and L5 regions, proving that the clouds were not just a trick of the eye, but real, physical structures. Now that we know the clouds are there, the next step is understanding their composition. Are they made entirely of lunar dust, kicked up by meteorite impacts and pulled into the Lagrange points? Or do they contain a mix of interplanetary material, collected over millions of years from passing comets and asteroids? If we could send a spacecraft to sample the dust in these clouds, we might be able to trace its origins, potentially unlocking secrets about the early solar system and the processes that shaped it. But getting to the Kordylewski Clouds is easier said than done. Unlike a planet or a moon, which provides a solid surface to land on, these clouds are vast, diffuse regions of space with no clear boundaries. A probe sent to study them would need to be designed in a way that allows it to collect dust particles without simply passing through empty space. One possibility is deploying a network of small satellites equipped with sensitive dust detectors, allowing us to map the density and composition of the clouds in detail. Beyond their scientific importance, the Kordylewski Clouds also raise interesting philosophical questions. Their existence challenges our perception of what it means for something to exist in space. Unlike planets, which are clearly defined objects, or stars, which emit light, these clouds are ephemeral, shifting, and almost ghost-like. They exist not as solid bodies, but as regions of influence, zones where dust gathers, lingers, and eventually disperses. They are a reminder that space is not empty, but filled with subtle structures that we are only beginning to detect. And this leads to another big question: are there even more of these hidden formations lurking in our own solar system? If the Kordylewski Clouds can exist in the Earth-Moon system, then similar dust formations could be found elsewhere. Could there be undiscovered dust clouds around Venus, Mars, or even Jupiter? Could Saturn's complex system of moons create stable Lagrange point dust clouds that have never been observed? As we push further into space exploration, understanding these hidden structures could become crucial. Spacecraft traveling through these regions might encounter unexpected dust concentrations, potentially posing risks to sensitive instruments. The presence of these clouds could also influence how we plan future lunar missions, satellite placements, and even space habitats. There's also a fascinating connection between the Kordylewski Clouds and the search for extraterrestrial life. If similar dust clouds exist around exoplanets, they might affect how we study distant worlds. Dust can absorb and scatter light, making it harder to analyze planetary atmospheres or detect biosignatures. Understanding the behavior of dust clouds around Earth could help us refine our methods for studying exoplanets, bringing us one step closer to answering the age-old question of whether we are alone in the universe. And yet, despite their potential importance, the Kordylewski Clouds remain one of the least studied aspects of near-Earth space. They are a reminder that even in our own cosmic neighborhood, there are still fundamental mysteries waiting to be unraveled. What else might be hiding in the gravitational shadows of our planet? What other unseen forces are shaping the space around us? The universe is full of secrets, and sometimes, the biggest mysteries are the ones that have been right in front of us all along. The Kordylewski Clouds remind us that space is not just about the massive, obvious celestial bodies like planets, moons, and stars. It is also about the delicate, nearly invisible structures that subtly influence our cosmic environment. These dust clouds are a testament to the complexity of orbital mechanics, showing that even tiny particles can be trapped in gravitational eddies for long periods. The fact that they remained unconfirmed for so long highlights how difficult it is to detect faint and diffuse structures in space, and it also raises the possibility that many more such formations could exist, waiting to be discovered. One of the most interesting aspects of these clouds is their dynamic nature. Unlike a planet or a moon, which follows a predictable path, the Kordylewski Clouds are constantly changing. Dust particles enter and leave the clouds as they are influenced by gravitational forces, solar radiation, and even the occasional interaction with Earth's magnetosphere. This means that while the clouds persist over time, they are not made up of the same particles at all times. Instead, they are an ever-changing collection of dust, replenished by cosmic events and dissipated by natural forces. The transient nature of these clouds raises important questions about their longevity. Are they truly stable over millions of years? Or do they only exist for certain periods before dispersing? Some scientists speculate that the Kordylewski Clouds might not be permanent structures but rather recurring formations that appear and disappear under specific conditions. This could explain why they have been so difficult to study. Perhaps they are not always there in the same density, and their visibility changes depending on how much dust is present at any given time. If this is true, then their existence could depend on external factors such as the sun's activity. The solar wind, a constant stream of charged particles emitted by the sun, could play a major role in shaping these clouds. During periods of high solar activity, the increased radiation pressure might push some of the dust out of the Lagrange points, causing the clouds to become less dense. Conversely, during periods of low solar activity, dust might accumulate more easily, making the clouds more prominent. This could mean that the Kordylewski Clouds follow a cycle, becoming more or less visible over time in response to the sun's changing behavior. The idea that the Kordylewski Clouds could be influenced by the sun's cycles leads to another intriguing question. Could they be used as natural indicators of space weather? If we could monitor these clouds over long periods, we might be able to detect patterns that correlate with solar activity. This could provide valuable insights into how the sun's energy affects the delicate balance of dust in our cosmic neighborhood. Space agencies already use satellites to monitor solar storms and their impact on Earth, but studying the Kordylewski clouds could offer a new way to observe how solar radiation influences objects in space over time. Another fascinating possibility is that the Kordylewski clouds might contain clues about ancient cosmic events. If these clouds have been accumulating dust for millions of years, then some of the particles trapped within them could be remnants of past celestial events, such as asteroid collisions or cometary debris. Studying the composition of these dust particles could reveal information about the history of our solar system, much like how ice cores on Earth provide records of past climate changes. To unlock these secrets, scientists would need to collect and analyze samples from the Kordylewski clouds. This would be a challenging mission, but not impossible. One approach could be to send a spacecraft equipped with specialized dust collectors to the L4 and L5 points, allowing it to capture and return samples to Earth for analysis. A mission like this could provide direct evidence of the cloud's composition, helping us determine whether the dust originates from the Moon, interplanetary sources, or even interstellar space. If some of the dust particles in these clouds come from beyond our solar system, it would open up an entirely new avenue of study. Interstellar dust is thought to be a carrier of complex organic molecules, the building blocks of life. If we could detect such molecules in the Kordylewski clouds, it would support the idea that the ingredients for life are not limited to Earth but are widespread throughout the universe. This could have profound implications for our understanding of the origins of life and the possibility of life elsewhere in the cosmos. Beyond their scientific significance, the Kordylewski clouds also have practical implications for future space travel. As humanity moves toward long-term space exploration, understanding the distribution of dust in near-Earth space becomes increasingly important. Spacecraft traveling through the L4 and L5 regions could encounter unexpected dust concentrations, which might pose risks to instruments and sensors. Space agencies need to factor in these hidden dust clouds when planning future missions, particularly those involving lunar exploration or space stations positioned at Lagrange points. Some researchers have even speculated that the Kordylewski clouds could be used in unexpected ways. For example, could they serve as natural shields against harmful cosmic radiation? Space radiation is one of the biggest challenges facing astronauts on long-duration missions, such as trips to Mars. If the Kordylewski clouds contain a significant amount of dust, they might act as a kind of buffer, absorbing some of the incoming radiation and providing a safer environment for spacecraft passing through. This is purely theoretical at this point, but it raises interesting possibilities for future space engineering. The discovery of the Kordylewski clouds also forces us to rethink our assumptions about what exists in the seemingly empty regions of space. If massive clouds of dust can remain hidden right next to Earth for so long, what else could be out there that we have yet to detect? Could there be even larger dust structures lurking in the solar system, undetected because of their faintness? Could similar formations exist around exoplanets, influencing their climates and atmospheres in ways we don't yet understand? These questions highlight the vastness of what we still don't know. Space is full of mysteries, and every new discovery opens the door to even more questions. The Kordylewski clouds, once thought to be a mere hypothesis, are now a confirmed reality, one that challenges our understanding of planetary dust dynamics and reveals the complexity of the gravitational interactions that shape our cosmic surroundings. As technology advances and our ability to observe space improves, we may finally be able to unlock the full story of these enigmatic clouds. Whether they hold the key to understanding the history of our solar system, offer insights into interstellar dust, or simply remind us of the unseen forces at work in space, one thing is clear: the Kordylewski clouds are more than just an obscure astronomical curiosity. They are a powerful reminder that even in the age of high-tech space exploration, the universe is still full of hidden wonders waiting to be discovered. The Kordylewski clouds stand as a testament to how much remains undiscovered in our own cosmic neighborhood. They are not just some obscure astronomical phenomenon. they challenge our perception of space itself. For centuries, we have envisioned space as a vast, empty void punctuated by planets, stars, and galaxies. But what if space isn't as empty as we think? What if it is filled with delicate, nearly invisible structures like these clouds, waiting to be uncovered? The fact that something as close as the Earth-Moon system could hide such a formation suggests that many more subtle cosmic features may exist beyond our current detection capabilities. One of the biggest questions surrounding the Kordylewski Clouds is how they interact with Earth's magnetosphere and surrounding space weather. Since these clouds reside at the L4 and L5 Lagrange points, they exist in a delicate gravitational equilibrium, meaning even small forces, like the solar wind or variations in Earth's magnetic field, could influence their shape and density. Some scientists have speculated that bursts of solar activity, such as coronal mass ejections, CMEs, could momentarily disrupt the clouds or even temporarily displace them. This would mean that these dust clouds are not just passive structures but dynamic entities that respond to changes in the space environment. If these clouds are indeed influenced by solar activity, then they could serve as natural laboratories for studying how dust behaves in microgravity under different space weather conditions. Understanding these interactions could have significant implications for spacecraft navigation and deep space exploration. For example, if future missions aim to place habitats or stations at the Lagrange points, knowing the density and movement of these dust clouds could help engineers design structures that can withstand long-term exposure to these environments. The potential presence of electrostatic forces within the Kordylewski Clouds is another aspect that has yet to be fully explored. In many space environments, dust particles become electrically charged due to exposure to ultraviolet light from the sun or interactions with plasma fields. If the dust in these clouds carries a charge, it could influence how the particles behave, potentially causing them to repel or attract one another in complex ways. This could explain why the clouds remain loosely bound instead of dispersing completely. Another area of interest is whether these clouds have a measurable impact on lunar dust transfer. Scientists have long been fascinated by the way dust moves between celestial bodies. The Moon, for instance, has no atmosphere to protect it from incoming micrometeorites, and as a result, its surface is constantly being bombarded by space debris. Some of this material is ejected into space and could potentially contribute to the dust content in the Kordylewski Clouds. If true, this would mean that the clouds act as a kind of temporary storage system for lunar material, cycling it through near-Earth space before it either falls back to the Moon, drifts toward Earth, or escapes into interplanetary space. The idea that the Kordylewski Clouds could contain a mix of terrestrial, lunar, and interstellar dust is especially intriguing. Each of these sources carries unique information about the history and evolution of our solar system. By analyzing the composition of the dust within these clouds, scientists could gain valuable insights into past asteroid collisions, the Moon's geological activity, and even ancient solar system events that left behind a cosmic dust signature. If interstellar dust is indeed present in these clouds, it would add another layer of mystery. Scientists already know that interstellar dust grains travel through our solar system, carried by the constant movement of the galaxy. Some of these particles have even been detected by spacecraft, such as NASA's Stardust mission, which captured tiny grains of interstellar material. But if the Kordylewski Clouds are collecting and holding onto some of this dust, they could represent an untapped scientific resource, a place where we could study material from beyond our solar system without having to launch an interstellar probe. This raises the question of whether these clouds could be natural traps for interstellar matter. The gravitational balance at the L4 and L5 points is such that objects can linger there for long periods, making these locations prime candidates for collecting drifting cosmic material. If these clouds have been around for millions of years, they might contain dust particles that predate our solar system, potentially offering clues about the raw materials that formed planets, moons, and asteroids. Another consideration is how these clouds might impact astronomical observations. Even though they are faint, they could contribute to a subtle background glow in certain wavelengths of light, particularly in infrared observations. Astronomers who study the cosmic background radiation or search for distant celestial objects might need to account for the presence of these dust clouds when interpreting their data. If the Kordylewski clouds scatter or absorb light in unexpected ways, they could influence our understanding of distant objects in space. In the future, as observational techniques continue to improve, we may develop new methods to study these clouds in greater detail. Space-based telescopes equipped with highly sensitive imaging technology could provide more precise measurements of their size, shape, and composition. Additionally, dedicated spacecraft missions could explore the L4 and L5 points directly, collecting in situ data that could help unravel the mysteries of these enigmatic formations. One idea that has been proposed is to send a small probe equipped with dust sensors and high-resolution cameras to fly through the clouds, capturing data on the movement and distribution of particles. Such a mission could determine whether the clouds are stable over time, or if they shift and change in response to external forces. This could also help answer the question of whether these clouds are unique to Earth, or if similar dust structures exist around other planetary systems. If Kordylewski clouds are common phenomena throughout the universe, they could reshape our understanding of how dust accumulates in space. Other planets with moons might also have similar dust clouds at their Lagrange points, forming natural reservoirs of material that could influence planetary evolution. If scientists find evidence of such formations elsewhere, it would suggest that dust clouds like these play a larger role in shaping planetary systems than previously thought. Beyond the purely scientific implications, the Kordylewski clouds also capture the imagination in a way that few other space phenomena do. They are invisible to the naked eye, yet they exist right in our cosmic backyard. They have remained hidden for most of human history, only to be confirmed in recent years. They represent a mystery that was overlooked for decades, proving that even in an age of advanced space exploration, some discoveries still require patience, creativity, and persistence. Ultimately, the Kordylewski clouds remind us that space is not just about the big, obvious objects. It is also about the delicate, transient structures that are easily overlooked. They challenge our assumptions about what can exist in space and encourage us to keep searching, keep questioning, and keep exploring. Because if these hidden clouds could exist so close to home for so long without being noticed, what else might be out there, waiting to be discovered? The Kordylewski clouds raise another fascinating possibility. Could they act as natural detectors for cosmic events? Because they are made up of fine dust particles that are sensitive to even the slightest perturbations in space, they could potentially record disturbances caused by passing asteroids, cometary debris, or even gravitational waves. If a massive object were to move through the L4 or L5 region, it might leave behind a subtle but detectable change in the distribution of dust within the clouds. Scientists could study these patterns to gain insights into recent cosmic interactions that would otherwise go unnoticed. This idea leads to another intriguing question. Could the Kordylewski clouds contain a record of past solar system events? Space is full of high-energy phenomena like gamma-ray bursts, supernova shockwaves, and solar storms. If the dust within these clouds has been accumulating for thousands or even millions of years, it may carry traces of these cosmic occurrences. By analyzing the elemental composition of the particles, scientists could determine whether the clouds have been exposed to radiation bursts or energetic cosmic rays in the past. This could provide a new way to study the long-term history of our solar system's interactions with the wider galaxy. In a way, the Kordylewski clouds could function as a sort of cosmic archive, preserving evidence of events that took place far beyond Earth's immediate vicinity. If dust from ancient supernovae has found its way into these clouds, it could offer an entirely new perspective on how interstellar material travels through space. It might also help answer one of the biggest questions in astrophysics: how much of the material in our solar system originates from external cosmic sources? If even a fraction of the dust in these clouds comes from outside our solar system, it would suggest that interstellar material moves between star systems more frequently than previously thought. Another curious aspect of the Kordylewski clouds is their potential connection to zodiacal light, a faint glow seen in the night sky, caused by sunlight scattering off interplanetary dust. Some researchers have speculated that these clouds could contribute to this glow in ways that haven't yet been fully studied. If the dust in these clouds has different optical properties than other interplanetary dust, it could subtly affect the way light is scattered in the inner solar system. This might help explain certain anomalies in zodiacal light observations that have puzzled astronomers for years. If the Kordylewski clouds are affecting light in unexpected ways, they could also play a role in another long-standing mystery, the so-called Pioneer anomaly. The Pioneer 10 and 11 spacecraft, launched in the 1970s, experienced a small but unexplained deviation in their trajectories as they moved through the outer solar system. Some scientists have wondered whether interactions with interplanetary dust could have played a role. If the Kordylewski clouds extend farther than we currently realize, they could be subtly influencing the motion of spacecraft, introducing small forces that accumulate over long distances. This leads to an even more profound implication. What if these clouds have been affecting spacecraft observations all along, without us realizing it? The orbits of satellites, probes, and even space telescopes depend on precise calculations of gravitational and atmospheric effects. If there is an additional, unaccounted-for source of dust around Earth, it might introduce tiny forces that could slightly alter the expected paths of these missions. Even though the effect might be small, over long distances, it could add up to measurable deviations. The existence of these clouds also raises another tantalizing question. Could they have played a role in Earth's past meteorological or climate patterns? While it might seem far-fetched, some scientists have proposed that large-scale dust clouds in space could have subtle effects on Earth's climate. If variations in the Kordylewski clouds cause changes in the amount of dust reaching Earth's upper atmosphere, they could influence cloud formation or even contribute to periodic cooling and warming trends. This idea remains speculative, but it underscores just how interconnected Earth's environment is with its cosmic surroundings. One of the most exciting possibilities is that the Kordylewski clouds might not be unique to Earth. If similar dust clouds exist at the Lagrange points of other planetary systems, they could represent a widespread but largely unnoticed feature of celestial mechanics. Planets with large moons, such as Jupiter's Europa or Saturn's Titan, might have their own versions of these clouds, potentially forming natural reservoirs of cosmic dust. If future missions to the outer solar system investigate these regions, they might discover structures similar to the Kordylewski clouds, hinting at a universal process that affects planetary systems throughout the cosmos. This could have significant implications for our search for extraterrestrial life. If Kordylewski-like clouds exist around exoplanets, they might serve as indicators of planetary conditions that are conducive to life. For instance, if a planet's dust clouds contain organic molecules or complex chemical compounds, they could provide clues about the presence of prebiotic chemistry in that system. Detecting such clouds around exoplanets could help scientists identify targets for future telescopic studies, guiding the search for habitable worlds beyond our own. Looking even further ahead, some researchers have suggested that the Kordylewski clouds, or similar formations, could be used as natural waypoints for space exploration. Since these clouds exist in relatively stable regions of space, they could serve as refueling stations or observation points for future deep space missions. If a spacecraft could harvest dust from these clouds, it might be able to extract useful materials for in-space manufacturing or fuel production. This could be a step toward a self-sustaining human presence in space, where natural resources are utilized to support long-term exploration efforts. Despite their potential significance, the Kordylewski clouds remain one of the least studied phenomena in near-Earth space. This is largely because they are difficult to observe, requiring highly sensitive instruments to detect their faint glow. But as technology advances, new tools, such as next-generation space telescopes and high-resolution imaging techniques, may allow scientists to probe these clouds in greater detail. Future missions could deploy specialized sensors to map their structure, density, and composition, shedding light on one of the most enigmatic features of our celestial environment. The Kordylewski clouds remind us of how much we still have to learn about the universe. Even in our own cosmic backyard, hidden structures continue to elude detection, waiting for the right moment, or the right technology, to reveal their secrets. They serve as a humbling reminder that science is an ongoing process, where every discovery leads to new questions, and every mystery opens the door to deeper understanding. The existence of these dust clouds challenges us to look closer, think bigger, and push the boundaries of what we know about the cosmos. What else might be hiding in the space around us? What other unseen structures are waiting to be discovered? The answer may be just beyond our reach, lingering in the shadows, waiting for us to turn our gaze in the right direction. The more we delve into the Kordylewski Clouds, the more they seem like a bridge between the familiar and the unknown. We tend to think of space as a vast emptiness, punctuated by planets, stars, and galaxies. But these clouds challenge that assumption. They exist in a liminal space, either a solid body like the moon nor a purely gravitational construct like an orbital path. Instead, they are something in between, an ephemeral, shifting presence that exists because of delicate cosmic balances. One of the most intriguing aspects of these clouds is the way they interact with solar radiation. Sunlight exerts pressure on everything it touches, and this is particularly significant for tiny dust particles. The force of solar radiation can slowly push dust in different directions, potentially altering the shape and density of the Kordylewski clouds over time. This raises a fascinating question: are the clouds stable, or are they constantly shifting, dispersing and reforming in cycles that we have yet to fully understand? If they do undergo periodic changes, what factors determine their lifespan? Could they one day dissipate entirely, only to reappear centuries later when conditions are just right? The idea that these clouds might be in constant flux opens up another possibility. What if they are influenced by solar storms and space weather? The Sun is not a passive sphere of light. It is an active, dynamic star that emits powerful bursts of charged particles in the form of solar wind and coronal mass ejections. When these solar storms reach Earth, they can disrupt satellites, cause power grid failures, and create dazzling auroras. But could they also affect the Kordylewski clouds? If a particularly strong solar storm were to sweep through the L4 or L5 regions, would it push the dust away, temporarily dispersing the clouds? Or could it, paradoxically, add more dust to them, trapping new particles in the gravitational dance between Earth and the Moon? If solar storms do have an impact, the Kordylewski clouds might act as a kind of natural barometer for space weather. By studying changes in their density and composition over time, scientists could gain a new way to monitor the long-term effects of solar activity on the space environment near Earth. This could be especially valuable as humanity becomes increasingly reliant on space-based infrastructure. If these clouds serve as a subtle but persistent record of solar conditions, they might help us predict future disturbances that could affect everything from GPS signals to astronauts' safety. Another question that arises when considering these clouds is whether they could play a role in the ongoing puzzle of space dust around Earth. Observations of the near-Earth environment have occasionally detected unexpected concentrations of fine particles, some of which seem to move in ways that are not entirely explained by known forces. Could the Kordylewski clouds be a missing piece of this puzzle? If they interact with other dust populations in the solar system, they might serve as a kind of gathering point, accumulating and dispersing particles in ways we haven't yet mapped. This possibility ties into a broader discussion in astrophysics about the movement of cosmic dust. We often think of planets, moons, and asteroids as the primary objects in our solar system, but dust is an equally important player. Tiny particles, barely larger than grains of sand, travel across vast distances, carrying information about the places they've been. Some of the dust in our solar system likely originated from ancient comet tails, asteroid collisions, or even interstellar space. If the Kordylewski clouds act as a kind of cosmic net, trapping and holding onto these particles, they could provide a unique window into the materials that drift through our region of the galaxy. What if, hidden within the dust of the Kordylewski clouds, there are particles that originated outside our solar system? The discovery of interstellar objects like Oumuamua and 2I/Borisov has shown that material from other star systems can, and does, enter our own. If even a fraction of the dust in these clouds has interstellar origins, it could help scientists learn more about the chemical makeup of distant worlds. This could be particularly valuable in the search for extraterrestrial life. If organic molecules or complex carbon structures were found in the dust, it might suggest that the basic building blocks of life are more widespread than we thought. This idea is further supported by the concept of panspermia, the hypothesis that life could spread between planets and star systems via space dust and meteorites. If the Kordylewski Clouds collect material from a variety of cosmic sources, they might contain clues about whether organic compounds can survive long journeys through space. Could these clouds serve as a kind of temporary storage system for biological material, transferring it between celestial bodies over time? While purely speculative, this possibility adds another layer of intrigue to their existence. There is also the question of how these clouds might evolve over extremely long time scales. The gravitational relationship between Earth and the Moon is not static. It changes over millions of years. The Moon is slowly moving away from Earth, altering the balance of forces that define the L4 and L5 points. Could this eventually lead to the Kordylewski Clouds dissipating altogether? Or might new conditions emerge that allow them to grow even larger? If these clouds have existed for millions of years, they might have witnessed dramatic shifts in Earth's climate, the Moon's orbit, and even the migration of asteroids through the inner solar system. All of this raises an important point. How much do we really know about our own cosmic neighborhood? The fact that something as large as the Kordylewski Clouds could go largely unnoticed for so long suggests that there may be other, even more mysterious structures lurking in the space around Earth. Could there be additional dust concentrations at other Lagrange points, waiting to be discovered? Might there be unknown gravitational interactions that create similar accumulations of material elsewhere in the solar system? These are questions that future space missions and advanced telescopic surveys may help answer. As technology improves, we may soon have the ability to study these clouds in ways that were previously impossible. Space probes equipped with ultra-sensitive dust detectors could fly through the L4 and L5 regions, directly sampling the particles within the clouds. High-resolution space telescopes could provide clearer images of their structure, revealing whether they are more diffuse or more concentrated than we currently believe. And advanced computer simulations could model how these clouds behave over time, helping us understand whether they are a transient phenomenon or a long-lasting feature of the Earth-Moon system. The Kordylewski Clouds are a perfect example of how the universe still holds countless secrets, even in places we think we know well. They challenge our assumptions about what exists in the space around us, inviting us to look closer, question more deeply, and rethink what we consider empty. They remind us that even in the age of advanced space exploration, we are still only beginning to scratch the surface of the cosmic mysteries that surround us. What other hidden structures might be lurking in our solar system? How many more discoveries are waiting just beyond the limits of our perception? The answers are out there, woven into the fabric of space itself, waiting for the day when we finally have the tools, and the curiosity, to uncover them. The deeper we explore the mysteries of the Kordylewski Clouds, the more we realize how little we truly understand about the space just beyond Earth. These clouds are not just a curiosity. They are a gateway to larger questions about dust dynamics, gravitational interactions, and even the long-term evolution of the Earth-Moon system. If something as large as these dust clouds could go largely unnoticed for decades, what else might be lurking in the cosmic shadows, waiting to be discovered? One of the biggest challenges in studying the Kordylewski Clouds is their elusive nature. Unlike planets, moons, or even asteroids, these clouds do not have a defined, solid shape. They shift, disperse, and reform depending on a delicate balance of gravitational forces, radiation pressure, and other cosmic influences. This makes them incredibly difficult to observe. Traditional telescopes struggle to detect them because they do not emit their own light. Instead, they can only be seen indirectly, either by how they reflect sunlight or by how they scatter light from other sources. Even then, their visibility is affected by Earth's atmosphere, which can distort or obscure their presence. This is why astronomers have turned to polarimetry, a technique that measures the polarization of light, to confirm the existence of the Kordylewski Clouds. Light waves normally oscillate in many directions, but when they scatter off certain particles, they become polarized, meaning their waves align in a specific pattern. By studying the polarization of light coming from the L4 and L5 points, scientists have been able to detect a distinct signal matching what would be expected from a large concentration of dust particles. This is a significant breakthrough, but it also raises new questions. If these clouds can be detected using polarization, could other, similar dust accumulations be found elsewhere using the same method? This opens the door to the possibility that the Earth-Moon system is not the only place where such clouds exist. Other planets in our solar system also have moons, and many of these planetary moon pairs have their own Lagrange points. If the right conditions are met, could similar dust clouds be forming around Mars and its moons, or around Jupiter and its many satellites? If so, these clouds could have significant implications for future space exploration. Spacecraft navigating these regions would need to account for the presence of dust, which could pose a hazard to sensitive instruments or solar panels. There's also the question of how the Kordylewski clouds interact with Earth's atmosphere over long periods. We know that Earth's atmosphere is not a static barrier, it constantly exchanges material with space. High-altitude winds, micrometeorite impacts, and even human-made satellites all contribute to a slow but steady exchange of particles between our planet and the surrounding space environment. If dust from the Kordylewski clouds occasionally drifts into Earth's atmosphere, could it leave behind any detectable signatures? Scientists have long studied the composition of atmospheric dust, searching for evidence of extraterrestrial particles. Some of this dust comes from comets, which shed tiny grains as they travel through the solar system. Some comes from asteroid collisions, and some may even come from interstellar space. If material from the Kordylewski clouds occasionally falls into Earth's upper atmosphere, it could provide a rare opportunity to analyze its composition without the need for a space mission. This could help answer one of the most fundamental questions: what exactly are these clouds made of? Understanding their composition is crucial because it could provide clues about their origins. Are the dust particles in these clouds primarily leftover debris from the early solar system, material that has been trapped in the Earth-Moon gravitational system for millions of years? Or are they constantly replenished by new material, perhaps from lunar dust ejected by micrometeorite impacts? If the latter is true, then the Kordylewski clouds could be part of a much more dynamic process, acting as temporary holding areas for dust that eventually settles back onto the Moon or falls toward Earth. This raises another fascinating possibility. Could the Kordylewski clouds play a role in the ongoing cosmic dust cycle of our solar system? We know that dust moves between planets, moons, and interplanetary space in complex ways, shaped by gravity, radiation, and even electromagnetic forces. If the Kordylewski clouds are a long-term feature of the Earth-Moon system, they might serve as a sort of dust reservoir, collecting and redistributing particles over time. This could have implications for everything from planetary formation theories to the potential spread of organic molecules across space. Another mystery surrounding these clouds is how stable they truly are. While recent observations have confirmed their existence, we do not yet have a complete understanding of whether they have been present for billions of years or if they form and dissipate on shorter timescales. If the latter is true, what triggers their formation, and what causes them to disperse? Could their presence be influenced by rare astronomical events, such as close passes of asteroids or shifts in the Moon's orbit? It's also worth considering the potential role of dark matter in this equation. Dark matter is one of the greatest mysteries in modern physics. We cannot see it directly, but we know it must exist because of its gravitational effects on galaxies and other cosmic structures. Some theories suggest that dark matter might not be entirely separate from ordinary matter, that it could interact with dust clouds, influencing their behavior in subtle but measurable ways. If the Kordylewski clouds are sensitive to gravitational forces beyond what we expect from just Earth and the Moon, could they serve as a kind of natural detector for dark matter? This idea is speculative but not entirely far-fetched. Some astrophysicists have proposed that cosmic dust could be influenced by hidden mass distributions in ways we don't yet understand. If dark matter interacts with dust in a way that alters its motion or clustering patterns, the Kordylewski clouds could provide an unexpected testing ground for these theories. Ultimately, the Kordylewski clouds represent just one piece of the puzzle when it comes to understanding our cosmic environment. They remind us that even in the space near Earth, an area we often assume is well mapped, there are still major discoveries to be made. Their existence challenges our understanding of how dust moves through space, how stable gravitational structures can shape matter, and how our own planet interacts with the wider solar system. As technology advances, new missions and telescopes will likely give us an even clearer picture of these elusive clouds. Perhaps future lunar missions will include instruments designed to study the dust around the Moon in more detail, confirming whether the Kordylewski clouds are connected to lunar material. Maybe an Earth-orbiting observatory will map their full extent, revealing previously unknown structures. There is even the possibility that one day, spacecraft might be sent to directly sample the dust within the clouds, bringing back material that could answer many of the questions we still have. Until then, the Kordylewski clouds remain one of the strangest, most mysterious features of the Earth-Moon system, a reminder that even in our own cosmic backyard, there are still secrets waiting to be uncovered. And if such an overlooked phenomenon can exist right next to Earth, what other cosmic structures might be hiding in plain sight? The mysteries surrounding the Kordylewski clouds extend far beyond their immediate presence in the Earth-Moon system. These vast, shifting dust clouds challenge fundamental ideas about orbital stability, cosmic dust behavior, and the delicate gravitational balancing act that occurs in celestial mechanics. Their very existence raises profound questions about what else might be lurking in the gravitational sweet spots of other planets, undetected by our current observational methods. One of the most intriguing aspects of the Kordylewski clouds is their role as an uncharted factor in Earth's near-space environment. When we think about the region around our planet, we tend to focus on satellites, space debris, and the occasional near-Earth asteroid. However, these massive dust accumulations introduce a new variable into the equation. Could they have an effect on spacecraft navigation? Could they pose an unrecognized challenge for future lunar missions or deep space probes that pass through their vicinity? The possibility that the Kordylewski clouds may interact with solar radiation and cosmic forces in unpredictable ways makes them a topic of interest for space exploration. Dust particles, even microscopic ones, can become electrically charged due to exposure to ultraviolet radiation from the sun. This means that the Kordylewski clouds could be influenced not only by gravitational forces but also by electromagnetic forces. If this is the case, then their structure may be more complex than a simple accumulation of dust. Instead, they could be dynamic, shifting in response to solar storms, changes in Earth's magnetic field, and even the solar wind. This has implications for space travel. If charged dust from the Kordylewski clouds interacts with spacecraft electronics, it could pose risks similar to those posed by static electricity or radiation exposure. While space agencies meticulously plan missions to avoid known hazards, the presence of large, unpredictable dust clouds could introduce unexpected variables. Future missions may need to account for the potential of encountering these dust regions, especially as human spaceflight expands beyond low Earth orbit. Furthermore, if the Kordylewski clouds are found to be electromagnetically active, this could have consequences for our understanding of space weather. Space weather, driven by solar activity, affects satellite communications, GPS systems, and even power grids on Earth. If these clouds interact with charged particles from the Sun, they could act as localized regions of disturbance, potentially influencing radio signals or altering the behavior of high-energy particles moving through the Earth's magnetosphere. This leads to another fascinating question: could the Kordylewski clouds be involved in a broader cosmic cycle of dust exchange? We know that Earth collects tons of cosmic dust every day, much of it from meteoroids that burn up in the atmosphere. Some of this dust settles onto the surface, contributing to the slow accumulation of extraterrestrial material on our planet. However, what if some of this dust is not simply falling into Earth but instead is temporarily getting trapped in the Kordylewski clouds? If this is the case, then these clouds could be acting as a kind of holding area for cosmic material before it eventually rains down on Earth. This concept has fascinating implications for astrobiology, the study of the origins of life in the universe. Some scientists have suggested that the early building blocks of life may have been delivered to Earth by comets or interstellar dust. If the Kordylewski clouds act as a reservoir for such material, they could be playing an unseen role in the long-term exchange of organic molecules between space and our planet. Could they be trapping and storing dust that contains amino acids, the fundamental components of life? Could they contain remnants of ancient cosmic events that predate the formation of our solar system? If this hypothesis holds true, then studying the Kordylewski clouds might not just be about understanding dust dynamics. It could be about unlocking secrets related to the very origins of life itself. Future space missions equipped with specialized instruments might be able to capture samples from these clouds, analyzing them for signs of complex molecules or even prebiotic chemistry. Beyond the biological implications, the presence of the Kordylewski clouds raises questions about the long-term evolution of the Earth-Moon system. If these dust clouds have existed for millions, or even billions, of years, then they could provide insights into how our planet's orbital environment has changed over time. Have they always been there, or do they come and go in cycles? Could their density fluctuate based on larger cosmic events, such as shifts in the Sun's activity or gravitational interactions with other celestial bodies? Some astronomers speculate that similar dust clouds might exist in the Lagrange points of other planetary systems. If the Earth-Moon system has maintained these clouds for so long, then it is possible that other moons around other planets have their own versions of the Kordylewski clouds. If we detect similar dust accumulations around exoplanets, it could provide a new way to study the orbital dynamics of distant worlds. In fact, if dust clouds exist in the Lagrange points of exoplanetary systems, they could serve as indirect indicators of exomoons, moons orbiting exoplanets. Right now, detecting exomoons is extremely difficult, as they are much smaller and fainter than the planets they orbit. However, if a distant exoplanet has stable dust clouds in its Lagrange points, it might suggest the presence of a moon that is helping to maintain them. This means that studying the Kordylewski clouds could have implications far beyond our own solar system. It could help refine our methods for detecting alien moons orbiting other worlds. Another mystery surrounding these clouds is their potential impact on Earth's atmosphere over long periods. We know that Earth's climate and atmospheric composition have changed drastically over millions of years. If the Kordylewski clouds have been a stable feature of the Earth-Moon system for that long, could they have had any subtle influence on our planet's climate? Some researchers have speculated that high-altitude dust layers can affect how sunlight is absorbed or reflected by the Earth. If the density of the Kordylewski clouds fluctuates over time, could it have had a minor but measurable effect on global temperatures or atmospheric chemistry? While this is still a speculative idea, it highlights how interconnected cosmic phenomena can be. Something as seemingly simple as a cloud of dust drifting in space could, in theory, have long-term effects on Earth's environment. This is why continued study of these clouds is so important. The Kordylewski clouds are a reminder that the space near Earth is far more complex than we once assumed. Their discovery and confirmation have opened up new avenues of research, from planetary science to astrophysics to space exploration. They challenge us to rethink our understanding of dust in space, gravitational stability, and even the potential for cosmic material to influence the evolution of planets. The more we learn about these clouds, the more questions we uncover. Are they unique to the Earth-Moon system, or are they a common feature of moon-planet pairs throughout the cosmos? Do they represent ancient remnants of the solar system's formation, or are they constantly replenished by new material? Could they hold clues about the origins of life, or even serve as unexpected indicators of dark matter? One thing is certain: the Kordylewski clouds prove that there is still so much to discover in our own cosmic backyard. If something as large and persistent as these dust clouds could remain unnoticed for so long, what other cosmic mysteries might still be hiding in plain sight, waiting for the right moment, or the right technology, to be revealed? The more we examine the Kordylewski clouds, the more they seem to be part of a hidden, overlooked aspect of our cosmic neighborhood. They sit in the delicate gravitational equilibrium of Earth and the Moon, hinting at a broader category of celestial structures that may exist undetected around other planetary systems. This raises the question: how many other dust clouds, rings, or particle accumulations might be hiding within the gravitational dance of moons and planets throughout the universe? If we take a step back and think about the role of Lagrange points in space dynamics, we start to see a pattern. These special points, where gravitational forces balance out, are natural gathering places for matter. In our own solar system, we already know of several places where material has collected due to these gravitational sweet spots. For example, Jupiter's Lagrange points host the Trojan asteroids, vast groups of space rocks that travel in lockstep with the gas giant, stable for millions, or even billions, of years. Could similar accumulations of dust exist around other planetary Lagrange points, just like the Kordylewski Clouds do for Earth and the Moon? If so, this could have significant implications for planetary science. Understanding how dust behaves in these stable regions could help us refine our models of planetary formation. In the early solar system, dust and gas gathered in certain areas, eventually forming planets, moons, and asteroids. If similar dust accumulations are found in other planetary systems, they could provide a window into the conditions that lead to the birth of planets. This would give us a new way to study planetary formation, by observing not just planets themselves, but the dust clouds that might surround them at key gravitational points. And yet, the Kordylewski Clouds remain an anomaly. Why are they not more widely discussed? Why have they remained so elusive, even in an age where we have telescopes powerful enough to peer into distant galaxies? Part of the reason is their nature. They are not solid objects like asteroids or moons, but diffuse, ever-shifting clouds of dust. This makes them difficult to detect with traditional methods. Unlike a planet or a moon, which can be directly observed through reflected sunlight, the Kordylewski Clouds are composed of tiny particles that scatter light in complex ways. Their faint glow is barely distinguishable from the surrounding background of space. It wasn't until relatively recently that modern scientific instruments confirmed their presence with certainty. This tells us something important. There may be many more faint, diffuse structures in space that we simply haven't discovered yet. The fact that something as large as these dust clouds could remain unconfirmed for so long suggests that space is full of overlooked phenomena. It also suggests that our current observational methods are still limited when it comes to detecting faint, ghost-like structures that do not emit their own light. This brings us to an even bigger question. What else could be hiding in the shadows of space, invisible to our current instruments? If the Kordylewski Clouds exist in Earth's gravitational field, could similar structures exist in the gravitational fields of other celestial bodies? Could Mars, Venus, or even exoplanets have their own versions of these dust clouds, orbiting silently, unseen by telescopes? One possibility is that the Kordylewski Clouds could be connected to a larger network of cosmic dust movements. Space is not empty, it is filled with interplanetary and interstellar dust, tiny particles that travel through the void, shaped by gravitational forces, solar radiation, and magnetic fields. If the Kordylewski Clouds interact with this larger flow of dust, they might not be static at all. They could be exchanging material with the broader interplanetary medium, acting as a temporary storage point for cosmic particles before they either drift away or fall to Earth. This raises another fascinating possibility. Could the Kordylewski Clouds contain material that originates from beyond our solar system? We already know that interstellar objects, like the mysterious Oumuamua, occasionally pass through our solar system. Likewise, interstellar dust continuously flows into our solar system from deep space. If some of this material gets trapped in the Kordylewski Clouds, then these clouds might serve as a collection point for cosmic debris that has traveled unimaginable distances. If we were able to collect and analyze dust samples from the Kordylewski Clouds, we might find material that predates the formation of our own solar system. We might find particles that originated in other star systems, or even remnants of ancient cosmic events, like supernovae that occurred billions of years ago. This would make the Kordylewski Clouds not just an Earth-Moon phenomenon, but a potential archive of the history of the cosmos itself. This possibility is why future space missions might need to take the Kordylewski Clouds more seriously. So far, most space exploration has focused on planets, moons, asteroids, and comets, solid objects that are easier to observe and interact with. But if the Kordylewski Clouds contain a mix of interplanetary and interstellar dust, then they represent a unique scientific opportunity. A spacecraft equipped with specialized instruments could fly through these clouds, collecting samples and analyzing them for clues about their origin. Imagine what we might find. Tiny grains of dust that contain isotopic signatures from stars that exploded billions of years ago. Organic molecules that might hint at the chemical precursors to life. Or even unexpected anomalies, materials that do not match anything we've ever seen before. This raises another, more speculative question. Could the Kordylewski clouds be a factor in the ongoing search for dark matter? Dark matter is one of the biggest mysteries in modern physics, an invisible substance that makes up most of the mass in the universe, yet does not emit or reflect light. Scientists have been searching for ways to detect dark matter, often by looking for its gravitational effects on visible objects. If dark matter interacts with normal matter in unexpected ways, could it be influencing the behavior of the Kordylewski clouds? Could these dust clouds be subtly shaped by an unseen gravitational force, providing indirect evidence of dark matter's presence? While this idea remains purely theoretical, it highlights just how many unanswered questions surround these clouds. They are not just a curiosity, they are an enigma that touches upon some of the most fundamental mysteries of space. And yet, despite all of this, the Kordylewski clouds remain largely unknown to the general public. They do not receive the same attention as black holes, exoplanets, or interstellar objects. Perhaps this is because they are not as visually dramatic as other space phenomena. They are not fiery supernovae or massive cosmic structures. They are subtle, fragile, and barely detectable. But in their own way, they are just as mysterious. They challenge our assumptions about what exists in space. They force us to reconsider the stability of dust in planetary orbits. They hint at connections between interstellar material and the Earth-Moon system. They suggest that cosmic dust may hold secrets we have not yet uncovered. As we continue to explore space, the Kordylewski clouds serve as a reminder that even the smallest, most unassuming structures can be part of something much greater. They are a piece of a vast cosmic puzzle, one that we are only just beginning to understand. And perhaps, in the years to come, they will reveal answers to questions we have not even thought to ask yet. The Kordylewski clouds may seem like a minor curiosity in the grand scheme of space exploration, but their existence raises fundamental questions about how dust, gravity, and cosmic forces interact on a scale we rarely consider. They challenge our understanding of orbital mechanics, the movement of interplanetary material, and even the boundaries of what we classify as a celestial body. Think about it. When we talk about space, we usually focus on the big things: planets, moons, stars, black holes. But the universe isn't just made up of massive objects. It's also filled with an uncountable number of tiny particles, drifting endlessly through the void. If we ignore these smaller elements, we might be missing out on key pieces of the puzzle that explain how our solar system formed and how celestial objects interact over time. In a way, the Kordylewski clouds could be thought of as a kind of fossil record in space. Unlike asteroids or moons, which move in predictable, stable orbits, these dust clouds are more fluid, shifting and evolving as they interact with solar radiation, gravitational forces, and even electromagnetic influences. Studying them could help us understand how dust behaves in low-gravity environments, which in turn might provide insights into planetary formation and even the conditions necessary for life to develop elsewhere in the universe. But here's where things get even more interesting. If the Kordylewski clouds exist in Earth's orbit, then could similar dust clouds be found around other planets in our solar system? Could Mars or Venus have their own versions of these mysterious accumulations? If so, they could be affecting space missions in ways we don't yet understand. Imagine a spacecraft traveling through what was assumed to be empty space, only to encounter an unexpected region of fine dust. Even a tiny amount of dust, traveling at high velocities, can pose a threat to spacecraft. If the Kordylewski clouds are denser in some regions, they could create hazards for future lunar missions or deep space travel. This means understanding their structure isn't just about satisfying scientific curiosity. It could be crucial for ensuring the safety of future space missions. And here's another possibility to consider. If dust can accumulate in these stable Lagrange points, what else might be hiding there? Could there be tiny asteroids or even artificial debris that has naturally settled into these regions over time? If so, the Lagrange points might be more than just theoretical balancing points. They could be natural collection zones for material drifting through the solar system. If we start looking at other planetary systems, this idea becomes even more fascinating. Astronomers are constantly searching for exoplanets. But what if exoplanets also have their own versions of the Kordylewski Clouds? If dust accumulates at the Lagrange points of exoplanetary orbits, it could affect how we detect and study those planets. In fact, some scientists have already considered the possibility that certain anomalies in exoplanetary observations might be due to the presence of similar dust structures. And what if these dust clouds contain more than just ordinary particles? If interstellar dust gets caught in the gravitational pull of the Earth-Moon system, then some of the material in the Kordylewski Clouds might not even be from our solar system at all. This opens up the possibility that these clouds are, in a way, cosmic archives. Collections of dust that have traveled across the galaxy, carrying information about their origins. Analyzing the composition of this dust could reveal traces of past supernovae, distant planetary systems, or even the chemical building blocks of life. If scientists were able to send a probe into the Kordylewski Clouds and retrieve a sample, we might gain direct physical evidence of material that originated in deep space. This could provide insights into the history of the Milky Way itself. And let's take this idea even further. Could there be unknown forces at play in maintaining these dust clouds? We usually think of gravity as the main force that governs celestial motion, but what if other forces, such as electromagnetic interactions, also play a role in keeping the Kordylewski Clouds in place? Space is full of charged particles, and the interaction between these particles and solar radiation creates complex electromagnetic fields. If the dust in the Kordylewski Clouds carries an electric charge, it could be affected by these fields in ways we don't fully understand. This could explain why the clouds remain stable despite the constant pull of gravity and the solar wind. This might also connect to larger questions about plasma physics and space weather. If the Kordylewski Clouds interact with charged particles from the Sun, they could provide a natural laboratory for studying how dust and plasma interact in space. This has implications for everything from understanding the behavior of dust in planetary rings to predicting how space weather might affect future space missions. It's strange to think that something as seemingly insignificant as a dust cloud could have such wide-reaching implications. And yet, the Kordylewski Clouds prove that even in the modern age, when we have satellites orbiting distant planets and telescopes peering into the farthest reaches of the universe, there are still things hiding right under our noses. Perhaps the biggest mystery surrounding the Kordylewski Clouds is why they have remained so obscure for so long. They were first suggested in the 1960s, but it wasn't until recent decades that their existence was confirmed. Why did it take so long for us to verify them? Part of the reason is that they are incredibly difficult to observe. Unlike planets or moons, which reflect light in a clear and detectable way, the Kordylewski Clouds are made up of tiny particles that scatter light unpredictably. They don't emit their own light, and their diffuse nature makes them hard to distinguish from the background of space. But this also raises another question. If they are this hard to see, what else might be hiding in space that we haven't discovered yet? Could there be other, even fainter structures in orbit around Earth that we haven't noticed? Could similar dust clouds be lurking in the gravitational fields of other celestial bodies? One of the most exciting possibilities is that future advancements in technology will allow us to map these kinds of structures in greater detail. With more sensitive instruments and new observational techniques, we might be able to create a more complete picture of how dust behaves in space. And if we can understand the Kordylewski Clouds, we might be able to apply that knowledge to a much broader range of astronomical questions. From planetary formation to interstellar dust transport, from space weather to the potential hazards of deep space travel, these clouds touch on a surprising number of scientific fields. Perhaps one day, the Kordylewski Clouds will no longer be a forgotten footnote in space science. Instead, they may be recognized as an important piece of the puzzle, one that helps us understand not just our own solar system, but the hidden forces that shape the universe itself. And as we continue to explore space, who knows what other unexpected discoveries are waiting to be made? The Kordylewski Clouds, despite their elusive nature, could be key to unlocking a deeper understanding of the forces that govern cosmic dust. Imagine a scenario where these dust clouds act as a kind of natural cosmic filter, capturing microscopic particles that have traveled for millions or even billions of years through space. These particles could hold clues about the chemical composition of other star systems, revealing the elemental building blocks of distant worlds. If we could analyze this interstellar dust, we might be able to determine whether the same chemical conditions that gave rise to life on Earth exist elsewhere in the universe. One of the biggest challenges in studying the Kordylewski clouds is their transient nature. Unlike a planet, which has a defined shape and structure, these clouds are constantly shifting. Dust particles move in and out, affected by the gravitational forces of the Earth, Moon, and Sun. This makes them incredibly difficult to map with precision. Some scientists even speculate that the Kordylewski clouds might have cycles of density, meaning they may appear and disappear over time. If this is true, then we might have only observed them during particularly dense phases, and they could sometimes be too diffuse to detect. This brings up another question: could these clouds eventually dissipate completely? If the dust within them is constantly being pulled away by solar radiation and gravitational forces, will they eventually thin out until they no longer exist? Or is there a constant supply of new dust replenishing them, keeping them stable over long periods? Understanding this balance could tell us more about the long-term dynamics of our planet's orbit and the movement of dust in the solar system. But let's take this concept a step further. If the Kordylewski clouds exist in the Earth-Moon system, could similar dust accumulations exist around other moons in our solar system? For example, Jupiter and Saturn have multiple moons and complex gravitational relationships. Could some of these moons have their own versions of Kordylewski clouds? If so, they might affect the way we observe and explore these planetary systems. For instance, if a spacecraft were sent to explore the region around Jupiter's moon Europa, and it encountered a previously undetected dust cloud similar to the Kordylewski clouds, it could change our understanding of how material moves in these systems. If these dust clouds exist around moons with subsurface oceans, they might even contain particles that hint at the presence of biological material, further fueling the search for extraterrestrial life. And speaking of extraterrestrial possibilities, what if advanced civilizations were aware of these kinds of dust accumulations and found ways to use them? Could a highly advanced species use these naturally occurring dust clouds as a form of camouflage, hiding probes or spacecraft within them? It sounds like science fiction, but space dust has unique properties that could be useful for stealth technology. A probe hidden within a diffuse cloud of dust would be nearly impossible to detect with conventional telescopes. This leads to another idea. If the Kordylewski clouds act as natural repositories for cosmic dust, could they also serve as traps for artificial debris? With the increasing amount of human-made objects in space, it's possible that tiny fragments of satellites or space missions have become caught in the gravitational balance of these clouds. If future missions were to study the Kordylewski clouds up close, they might not only find interstellar dust but also remnants of past space missions that have become permanently embedded in these orbital regions. One of the more practical implications of studying the Kordylewski clouds is understanding how dust affects optical and radio signals. Space-based telescopes and communication satellites rely on clear transmission paths, but if dust clouds exist in stable orbital regions, they could scatter signals in unpredictable ways. This could have subtle effects on astronomical observations, especially those involving faint light sources or deep space radio signals. In a broader sense, the study of cosmic dust, including the Kordylewski clouds, ties into some of the most fundamental questions in astrophysics. How do planetary systems form? How does interstellar material move through the galaxy? Could the same mechanisms that allow dust to accumulate in stable orbital positions also lead to the formation of entire planets? One possibility is that studying these dust clouds could provide insight into the early stages of planetary formation. When a solar system is in its infancy, it consists mostly of gas and dust, much like the Kordylewski clouds. Over time, this material begins to clump together, forming larger and larger objects until planets and moons emerge. By examining how the Kordylewski clouds maintain their structure, we might gain clues about how young solar systems evolve. This idea is especially intriguing when considering exoplanets, planets beyond our solar system. If other planetary systems have similar dust clouds in their Lagrange points, they might affect how we detect and study those exoplanets. In some cases, these dust accumulations could make it harder to see a planet, obscuring its light and making observations more challenging. In other cases, the dust could act as a natural amplifier, scattering light in ways that make planets easier to detect. In the future, as space telescopes become more advanced, we might be able to detect Kordylewski-like dust clouds around exoplanets. If these clouds exist in multiple star systems, it could indicate that dust accumulation at Lagrange points is a common feature of planetary orbits. This would be a groundbreaking discovery, as it would suggest that the conditions for planetary formation and dust dynamics are universal across the cosmos. The more we look into the Kordylewski clouds, the more questions arise. Could they be influenced by dark matter, the mysterious substance that makes up most of the universe's mass but remains invisible to us? If dark matter interacts with ordinary matter in ways we don't yet understand, it could be playing a role in stabilizing these clouds. Some theories even suggest that regions of space with dense dust clouds could act as natural detectors for dark matter interactions, potentially offering a new way to study this elusive phenomenon. Another unexplored possibility is whether the Kordylewski clouds could have any impact on Earth's climate. While they are far too diffuse to block sunlight in any noticeable way, they might interact with cosmic rays or solar radiation in ways we haven't yet studied. If these dust clouds have even a minor effect on the space environment around Earth, they could play a small but measurable role in long-term climate patterns or atmospheric chemistry. As we continue to explore space, the Kordylewski clouds stand as a reminder that some of the biggest mysteries aren't necessarily found in the farthest reaches of the cosmos. They might be right next to us, hiding in plain sight. What else might we be overlooking? Could there be other unknown structures orbiting Earth, waiting to be discovered? Perhaps in the near future, new space missions will finally provide definitive answers about the Kordylewski clouds. Advanced space telescopes, deep space probes, or even crewed missions to the moon might gather new data on these enigmatic dust accumulations. Until then, the Kordylewski clouds remain one of space's most overlooked mysteries, a silent, shifting presence in Earth's orbit, hinting at deeper cosmic secrets yet to be unraveled. Continuing the exploration of the Kordylewski clouds, we must ask a fundamental question: why have they remained so elusive despite their proximity to Earth? Unlike distant galaxies or black holes, which require powerful telescopes to observe, these dust clouds exist relatively close to our planet. Yet, for decades, their very existence was debated. This suggests that their visibility is highly dependent on environmental factors, such as the angle of sunlight, atmospheric conditions, and even the way light scatters through interplanetary space. One reason for their elusive nature is that they don't emit their own light. Unlike planets or stars, which either reflect or generate visible radiation, the Kordylewski clouds primarily scatter sunlight. This makes them incredibly difficult to detect unless the conditions are just right. It's similar to how you can sometimes see dust floating in the air when a beam of sunlight enters a dark room. Without the right lighting, the particles are practically invisible. Even when scientists attempt to observe them with specialized instruments, the challenge remains. The dust in these clouds is incredibly fine, meaning that even the most advanced telescopes struggle to distinguish them from the general background noise of space. This has led to some skepticism about their existence, with some researchers arguing that they might not be stable structures but rather temporary accumulations of dust that come and go. Yet, multiple observations over the years suggest otherwise. In 2018, a team of Hungarian astronomers provided some of the strongest evidence yet that these clouds do exist. Using polarimetric imaging, an advanced technique that detects light scattered by small particles, they were able to observe patches of dust in the predicted locations of the Kordylewski clouds. This confirmed that something was there, but it also raised new questions. If the clouds are real, how long have they been around? Did they form recently, or have they been a feature of Earth's orbit for millions of years? If they are long-lived, then they might have played a role in the history of our planet in ways we have yet to understand. One possibility is that these clouds could have served as a temporary holding ground for meteoric material before it eventually fell to Earth. Throughout history, Our planet has been bombarded by space rocks, some of which have had profound effects on life. If the Kordylewski Clouds have existed for millions of years, then they might have influenced the distribution of these impacts by acting as a sort of cosmic net, trapping small objects before they either drifted away or were eventually pulled in by Earth's gravity. But this raises another question: what if the dust within the Kordylewski Clouds contains fragments of material from outside our solar system? Interstellar objects, like the recently detected Oumuamua, occasionally pass through our planetary neighborhood. Could some of these foreign particles become caught in the gravitational balance of the Earth-Moon system, ending up trapped in the Kordylewski Clouds? If this is the case, then studying these clouds could provide a unique opportunity to examine material from other star systems without having to send probes vast distances into deep space. A spacecraft could theoretically be sent to these dust clouds, collect samples, and bring them back to Earth for analysis. If we were to find elements or isotopic ratios that don't match anything found in our solar system, it would be strong evidence that material from other stars has made its way into our orbit. This also ties into the idea that the Kordylewski Clouds could hold clues about the origins of life. Some scientists propose that organic molecules, or even primitive life forms, could travel between planets and star systems on meteors and dust grains. This concept, known as panspermia, suggests that the building blocks of life might not have originated on Earth but were instead delivered by cosmic debris. If the Kordylewski Clouds act as a collection zone for interstellar material, they could contain microscopic traces of organic molecules that formed elsewhere in the galaxy. If future missions discover such molecules within these dust clouds, it would raise profound questions. Could similar dust clouds around other planets or moons serve as reservoirs for life's ingredients? If so, could habitable worlds be seeded with organic material in this way? These are questions that could redefine how we think about the potential for life beyond Earth. Another mystery surrounding the Kordylewski Clouds is how they interact with the Earth-Moon system over time. Since they are located in Lagrange points, regions of gravitational stability, they should, in theory, remain in place indefinitely. But we also know that the Moon is slowly drifting away from Earth, moving about 3.8 centimeters per year. Over millions of years, this gradual shift could change the gravitational balance of the system, potentially affecting the structure and stability of these dust clouds. As technology advances, we may finally be able to study these clouds in greater detail. Upcoming space missions, such as those involving the Artemis program, could provide new opportunities to observe them up close. The Moon serves as a perfect vantage point for observing these clouds without interference from Earth's atmosphere. Future lunar missions could deploy telescopes or instruments designed specifically to analyze the dust composition of these clouds and determine their exact structure. One potential benefit of understanding the Kordylewski Clouds is that it could improve our knowledge of space weather. Cosmic dust interacts with solar radiation, magnetic fields, and charged particles from the Sun. If these clouds have any influence on the way radiation reaches Earth, they could play a small but measurable role in our planet's space environment. This could be especially relevant as humans prepare for longer-duration space travel. Spacecraft traveling beyond Earth's immediate orbit will encounter various forms of dust, radiation, and other cosmic hazards. If dust clouds like the Kordylewski Clouds exist elsewhere in the solar system, they could pose navigational challenges or even opportunities for resource collection. For example, if a mission to Mars were to pass through a previously undetected dust accumulation at a Lagrange point, it might need to adjust its trajectory to avoid potential damage to sensitive instruments. Conversely, if a spacecraft could collect useful materials from such clouds, it might reduce the need for carrying extra resources from Earth. Ultimately, the Kordylewski Clouds remain one of the most fascinating and underexplored features of our cosmic neighborhood. Their study could bridge multiple scientific disciplines, from astrophysics to planetary science to the search for life beyond Earth. Each new piece of evidence brings more questions, fueling the curiosity that drives space exploration. What other hidden structures might be lurking in our orbit, waiting to be discovered? Could there be additional, undiscovered dust clouds in other stable orbital positions? And if so, what secrets do they hold about the formation of planetary systems, the movement of interstellar material, and the potential for life beyond our world? As scientists continue their search, one thing remains certain: the universe is full of mysteries, and some of the most intriguing ones might be right in our backyard, hiding in the faint, shifting dust of the Kordylewski Clouds. The study of the Kordylewski Clouds is just beginning, and as technology improves, we will likely uncover more about their nature, composition, and possible implications for science. But beyond their immediate physical characteristics, these clouds could also play a role in deeper cosmic mysteries, ones that touch on the fundamental structure of our universe, the origins of life, and the strange interplay between matter and gravity in space. One of the most intriguing aspects of these clouds is their position at the L4 and L5 Lagrange points. These points are not just random locations in space. They represent regions of equilibrium where gravitational forces balance out in such a way that objects can remain stable for extended periods. This makes them particularly interesting not just for natural formations like the Kordylewski Clouds but also for potential space missions and future human expansion beyond Earth. If dust can accumulate and persist in these locations, could other materials as well? Some researchers have speculated that Lagrange points might act as natural storage areas for debris, asteroids, or even artificial objects over long periods. This raises the possibility that other, yet undiscovered clouds of dust or rock might exist in our solar system, hidden within similar gravitationally stable zones. More intriguingly, Lagrange points are also considered prime locations for space colonies or deep space observation platforms. The stability of these points means that spacecraft placed there wouldn't need to use as much fuel to maintain their position, making them ideal locations for long-term observation stations or even lunar bases. The presence of the Kordylewski Clouds, however, introduces a new consideration. How would the constant presence of fine dust affect instruments, solar panels, or human habitats in these regions? Would future space stations at L4 or L5 need protective shielding to prevent dust accumulation? Could the clouds interfere with radio signals or other forms of communication? These are practical concerns that researchers will need to address as space exploration moves forward. Beyond their implications for space travel, the Kordylewski Clouds might also hold clues about larger cosmic phenomena. Dust in space doesn't just sit passively, it interacts with electromagnetic radiation, gravitational forces, and even cosmic magnetic fields. Understanding the behavior of the dust in these clouds could offer insights into how similar materials behave throughout the galaxy. For example, one of the biggest unsolved mysteries in astronomy is the presence of dark matter, an invisible substance that appears to make up most of the mass in the universe but does not emit or interact with light in a way we can directly detect. While the Kordylewski Clouds are made of ordinary dust, studying them might provide new ideas for how weakly interacting particles behave in space. Some researchers have even proposed that dark matter itself might form similar clouds in galaxies, accumulating in stable regions and subtly influencing the motion of stars and planets. Could studying the dynamics of the Kordylewski Clouds provide a small-scale model for understanding larger cosmic structures? Additionally, if these clouds contain interstellar material, as some researchers speculate, they could serve as a kind of natural archive, preserving dust and particles from various epochs of the solar system's history. By analyzing these materials, scientists could piece together clues about past cosmic events, such as supernova explosions that might have seeded our solar system with heavy elements. This brings us back to the possibility that the Kordylewski Clouds might contain remnants of ancient celestial events. If we could retrieve and analyze samples from these dust clouds, we might uncover evidence of past planetary collisions, remnants of comets that have disintegrated over time, or even rare isotopic signatures from distant supernovae. One of the biggest challenges in studying these clouds is that their faint nature makes them difficult to detect with traditional observational methods. However, advancements in space telescopes, spectroscopy, and artificial intelligence-driven data analysis might change that. Future missions could use ultra-sensitive light detectors or specialized instruments designed to analyze the way dust scatters light in microgravity. Moreover, private space companies are beginning to play a bigger role in space exploration, opening up new possibilities for investigating these clouds. With more frequent lunar missions, asteroid mining projects, and even deep space probes being planned, there could soon be an opportunity to send dedicated missions to the L4 and L5 points to study the Kordylewski Clouds up close. A probe designed to navigate through these dust clouds could collect particles, analyze their chemical composition, and provide real-time data on their structure and movement. This would not only confirm their existence beyond any doubt but also help answer key questions about their origin and evolution. If interstellar dust is found within the Kordylewski Clouds, it would also support the theory that material from other star systems can find its way into stable pockets of space within our own solar system. This could mean that Earth, and possibly other planets, have been receiving cosmic visitors in the form of microscopic particles for billions of years. Could life itself have arrived on Earth this way? Some scientists believe that simple organic molecules, or even the precursors of life, could survive the journey through space, protected within grains of dust or ice. If we find such molecules within the Kordylewski Clouds, it would lend credibility to the idea that the ingredients for life are widespread in the cosmos. This also raises another question. Could other planets or moons in our solar system have similar dust clouds? If so, could these regions be potential targets for future missions searching for signs of life? Studying the Kordylewski Clouds could be a stepping stone to a much broader understanding of how materials move through space, how solar systems exchange matter, and even how life might spread from one world to another. There's also the question of whether these dust clouds have any noticeable impact on Earth itself. While they are far too diffuse to block sunlight in any meaningful way, they could still have subtle effects on Earth's atmosphere or magnetosphere. Some researchers have speculated that these clouds might contribute to space weather phenomena, influencing the movement of charged particles from the Sun. Additionally, their presence raises the possibility that similar dust clouds might exist around other planets in our solar system. If Mars, Venus, or even some of Jupiter's moons have their own Kordylewski-like dust clouds, it would suggest that this is a common feature in planetary systems. As the search for exoplanets continues, astronomers have begun to consider whether dust clouds like these could exist in other star systems. If an Earth-like planet in another system has its own version of the Kordylewski Clouds, they could serve as a detectable signature of a stable planetary environment. This is particularly relevant when searching for habitable worlds. If dust clouds are common around certain types of planets, they could provide clues about the gravitational interactions happening in those systems. More importantly, they might also contain evidence of planetary formation, revealing how young planets accumulate material and grow over time. In the coming years, new space telescopes like the James Webb Space Telescope and future generations of observatories will be able to study these phenomena in greater detail. As we refine our ability to detect faint objects in space, we might find that Kordylewski-like clouds exist in more places than we ever imagined. The more we learn about these mysterious dust formations, the more they seem to connect to larger questions in astronomy, planetary science, and even astrobiology. From their elusive nature to their potential role in transporting cosmic materials, the Kordylewski Clouds represent a hidden aspect of our celestial neighborhood that could reshape how we think about Earth's place in the cosmos. But the biggest question remains: what other hidden structures might be lurking in the gravitational shadows of our solar system? Could there be more undiscovered features at other Lagrange points, waiting for us to notice them? And if so, what secrets do they hold about the history and future of our world? As scientists continue to probe these mysteries, one thing is certain: the universe is full of surprises, and the more we look, the more we find. The Kordylewski Clouds, despite being faint and difficult to detect, could be just one piece of a much larger puzzle, one that challenges our understanding of how dust, gravity, and celestial mechanics interact on both small and cosmic scales. If these clouds have existed for millions of years, and if similar structures exist around other planets, or even in interstellar space, what else might be out there that we've yet to discover? One of the more fascinating aspects of these clouds is their apparent stability. Traditional thinking suggests that dust should eventually disperse due to solar radiation pressure, the gravitational influence of other bodies, and interactions with the solar wind. And yet, the Kordylewski Clouds persist, indicating that the delicate balance of forces at the L4 and L5 points is stronger than we might have assumed. This raises an interesting question. Could these clouds act as natural collectors of cosmic debris? If they are able to hold on to dust for long periods, they might serve as a kind of astronomical time capsule, preserving materials from ancient asteroid collisions, cometary remnants, or even interstellar particles that have drifted into our solar system. If we could send a probe to these clouds and collect samples, we might uncover microscopic particles that tell a story stretching back to the early formation of the solar system. Could there be traces of ancient supernovae, scattered across the galaxy and trapped in these stable regions? Could the very building blocks of life, the organic molecules necessary for biology, be hidden within these clouds? The possibility that the Kordylewski clouds might contain organic compounds is an exciting one. We already know that organic molecules exist throughout space, from the surfaces of asteroids to the atmospheres of distant planets. If these molecules are present in the dust of the Kordylewski clouds, it could support the theory of panspermia, the idea that life, or at least the ingredients for life, can spread between planets and even star systems. The notion that dust clouds might play a role in distributing the building blocks of life across the cosmos is a topic of serious scientific interest. If these clouds contain amino acids, complex hydrocarbons, or other prebiotic materials, they could serve as a mechanism for spreading life-friendly chemistry across the solar system. This would mean that Earth might not be unique in its potential to develop life. Other planets with similar dust clouds might have had access to the same ingredients. And if the Kordylewski clouds are just one example of such a structure, how many others might be out there, waiting to be discovered? Could there be similar clouds at the Lagrange points of other planets, each one holding its own unique collection of cosmic materials? Could these clouds serve as a kind of interplanetary transport system, slowly exchanging material between worlds over millions of years? One of the challenges in studying the Kordylewski clouds is their extreme faintness. Because they consist of loosely scattered dust, they do not reflect much light, making them almost invisible against the backdrop of space. However, advances in optical and infrared astronomy might soon allow us to map these clouds with much greater accuracy. Future space missions, equipped with highly sensitive instruments, might be able to perform a detailed survey of the L4 and L5 regions. If they confirm the existence of stable dust clouds, they might also uncover new details about their composition, motion, and potential interactions with Earth's environment. This brings up another interesting possibility. Could the Kordylewski clouds influence Earth's climate in any way? While the amount of dust is likely too small to have a significant effect, even subtle interactions between space dust and Earth's atmosphere could be worth investigating. Some scientists have suggested that dust particles in space can serve as nuclei for ice crystal formation, potentially playing a role in cloud formation at high altitudes. If the Kordylewski clouds shed dust that drifts toward Earth, could it have any measurable impact on weather patterns or long-term climate trends? This idea remains speculative, but it points to a larger truth. There is still so much we don't know about how cosmic dust interacts with our planet. Every day, Earth is bombarded with micrometeorites and space dust, much of which burns up harmlessly in the atmosphere. But what if certain stable dust clouds, like the Kordylewski clouds, serve as long-term reservoirs of material that occasionally contribute to these influxes? Another key mystery is whether these clouds are entirely natural or if there are any artificial influences affecting them. With the growing number of satellites, space debris, and human-made objects in orbit, could our own technological activity have any impact on the stability or composition of these clouds? As space travel expands and humanity moves toward permanent settlements beyond Earth, understanding the full scope of our solar system's dust environment will become increasingly important. If the Kordylewski clouds contain fine particles that could pose a risk to spacecraft, or if they could interfere with certain types of communications, they will need to be factored into mission planning for deep space travel. There is also the question of whether the Kordylewski clouds might provide any practical benefits. Could they be used as natural shielding zones against cosmic radiation? If these dust clouds are dense enough, they might help block some of the high-energy particles that pose a risk to astronauts and spacecraft. Alternatively, if the dust contains useful materials, such as rare metals or isotopes, it might one day be possible to mine these clouds for resources. While this idea is purely theoretical for now, the increasing interest in space mining means that no potential resource should be overlooked. And yet, despite their many scientific implications, the Kordylewski Clouds remain one of the most elusive features of our celestial neighborhood. Unlike planets, moons, or even asteroids, these clouds are almost intangible, structures that exist on the edge of visibility, only revealing themselves under the right conditions. They remind us that even in our own solar system, mysteries still abound. There are forces at play that we have yet to fully understand, hidden interactions between dust, gravity, and light that could reshape our understanding of celestial mechanics. The fact that the Kordylewski Clouds were first predicted decades ago, but only recently confirmed, serves as a humbling reminder that science is always evolving. What else might be lurking in the shadows of our planetary system, waiting for the right observer, the right technology, or the right moment to be discovered? Could there be even larger, more massive dust structures hidden in the gravitational corridors of our solar system? Are there undiscovered particles, unknown physical interactions, or unexpected phenomena associated with these clouds? As our exploration of space continues, the Kordylewski Clouds will likely move from being an obscure astronomical curiosity to an important subject of research. They represent a frontier, one that challenges our ability to detect the faintest whispers of cosmic activity and pushes the boundaries of what we consider to be a planetary feature. They also serve as a symbol of the universe's ability to surprise us. In a time when we have mapped distant galaxies, observed black holes, and sent probes beyond the edge of the solar system, there are still fundamental aspects of our own cosmic backyard that remain unknown. But perhaps that is what makes space so endlessly fascinating. The more we discover, the more we realize how much is still left to uncover. And the Kordylewski Clouds, drifting silently at the edges of Earth's gravitational influence, remind us that even the most familiar parts of the cosmos can still hold secrets beyond our wildest imagination. The very existence of the Kordylewski Clouds forces us to rethink what we know about Lagrange points and how celestial bodies interact in these gravitationally stable regions. If dust can persist at L4 and L5 for extended periods, it raises an even bigger question. Could there be even larger, more stable accumulations of material elsewhere in the solar system that we haven't yet detected? Consider the possibility that other planets, especially those with large moons, might have their own versions of Kordylewski Clouds. Jupiter, with its immense gravitational influence and multiple moons, could be home to dust clouds that dwarf those near Earth. If similar clouds exist around Mars, Saturn, or even exoplanets beyond our solar system, it might reveal an entirely new category of celestial structures, stable dust formations that act as natural records of cosmic history. The implications of this are staggering. If dust accumulates in these stable regions over millions or even billions of years, it could preserve evidence of past cosmic events, asteroid collisions, cometary activity, and even interstellar material that has drifted into our solar system. The Kordylewski Clouds could be part of a much larger, hidden system of dust reservoirs that exists throughout the cosmos. But this also raises another important question: how do these clouds form in the first place? While we know that the L4 and L5 points are regions of gravitational equilibrium, the process by which dust gathers and remains in these spots is still not entirely understood. Some scientists speculate that these clouds might have formed gradually, accumulating dust from the moon, the solar wind, and even micrometeorite impacts over millions of years. Another intriguing possibility is that these clouds are replenished by some unknown mechanism. If they were merely ancient accumulations of dust, one might expect them to slowly dissipate over time. But the fact that they still exist suggests that either new dust is continuously being added or that some force, perhaps an unexpected gravitational interaction, is helping to keep them intact. Could the moon play a role in maintaining these clouds? We know that lunar dust can be ejected into space due to micrometeorite impacts. Some of this dust might drift toward the Kordylewski Clouds and become trapped in the stable Lagrange regions. If this is the case, then the Kordylewski Clouds could be directly linked to lunar activity, acting as a kind of secondary dust belt influenced by the moon's surface interactions. This also leads to another fascinating hypothesis. What if the Kordylewski clouds are not entirely passive structures, but dynamic environments that shift and change over time? Instead of being static formations, they might experience fluctuations in density, size, and composition based on solar activity, Earth's orbital changes, and gravitational influences from the Moon and other celestial bodies. If this is true, then the Kordylewski clouds might not always be the same. They could grow and shrink, appearing and disappearing over different time scales. This would explain why they have been so difficult to observe consistently, as their visibility might depend on their current density and position relative to Earth and the Sun. The idea that space contains hidden, fluctuating structures is not entirely new. Scientists have long suspected that our solar system is filled with transient dust clouds, temporary accumulations of particles that form under specific conditions before dispersing. The Kordylewski clouds might be just one example of this phenomenon, a small piece of a much larger network of dust reservoirs that constantly shift and evolve. If we could study these clouds in greater detail, we might learn not only about their composition but also about the forces that shape them. What if the solar wind, a constant stream of charged particles from the Sun, plays a role in influencing their structure? Could electromagnetic forces be at work, subtly affecting how the dust particles interact with each other? There's also the possibility that the Kordylewski clouds might be part of a larger, previously undetected dust ring around Earth. Some researchers have speculated that Earth might have a thin, nearly invisible ring of dust similar to those found around other planets like Jupiter and Saturn. If this is the case, the Kordylewski clouds could be just the densest regions of this larger structure, acting as focal points where dust accumulates due to gravitational and electromagnetic interactions. This idea would not only change our understanding of Earth's near-space environment, but also raise new questions about how our planet interacts with cosmic dust on a broader scale. Could this hypothetical dust ring influence Earth's atmosphere or climate in subtle ways? Could it play a role in the way our planet interacts with interstellar particles that drift through the solar system? These are questions that remain unanswered, but they highlight just how little we know about the hidden structures that might exist right in our cosmic backyard. The Kordylewski clouds might be just the beginning, a small clue pointing toward a much greater and more complex system of celestial interactions that we have yet to fully understand. And then there's the question of what these clouds might look like up close. If an astronaut were to travel to the L4 or L5 point and enter one of these clouds, what would they see? Would the dust be dense enough to create a visible haze, or would it be so sparse that it would only be detectable with instruments? Some scientists speculate that within these clouds, light scattering effects might create strange optical illusions, similar to the way atmospheric dust can cause halos and glows around the Sun and Moon. If this is the case, then the Kordylewski clouds might not only be scientifically interesting but also visually stunning, ethereal regions of space where light behaves in unexpected ways. If future missions explore these clouds, they might use specialized imaging techniques to capture their structure in unprecedented detail. High-resolution cameras, dust analyzers, and even artificial lighting could be used to reveal their true form. Would they appear as ghostly, swirling formations, or would they be more like faint, invisible veils drifting through space? And if we do send spacecraft to these clouds, what might we find hiding within them? Could there be particles from beyond our solar system, remnants of distant cosmic events that have slowly made their way to this gravitationally stable region? Could we uncover new clues about how dust behaves in space, leading to insights that could improve our understanding of planetary formation, asteroid dynamics, and even interstellar travel? One thing is certain: the Kordylewski clouds represent a mystery that refuses to be ignored. Their mere existence challenges long-standing assumptions about how dust moves through space, how Lagrange points function, and how celestial bodies interact with their surroundings. They are a reminder that even in an age of powerful telescopes and space exploration, there are still fundamental aspects of our own cosmic neighborhood that remain largely unknown. And perhaps that is what makes them so fascinating. The more we learn about them, the more questions arise. They are a doorway to new discoveries, a tantalizing hint that our understanding of space is still incomplete. The universe is filled with mysteries, some grand and distant, others surprisingly close to home. The Kordylewski Clouds are one of those enigmas, a whisper of the unknown, waiting for us to listen. The idea that the Kordylewski Clouds could be dynamic structures, constantly shifting and evolving, adds a whole new layer of intrigue to their existence. If these clouds are not static but fluctuate in density and position, then every observation we make could capture them in a different state. One year they might be barely detectable, and the next, they could appear denser than ever. This could explain why some astronomers struggled to confirm their existence for so long. If they behave like cosmic mirages, sometimes present, sometimes fading into near invisibility, then our understanding of them must account for this variability. One possible reason for their fluctuating nature could be the influence of the solar wind. The sun constantly emits charged particles in all directions, creating a powerful force that interacts with everything in the solar system. If the Kordylewski Clouds are composed of tiny dust particles, then they are likely affected by these solar emissions. The question is, how much? Could the solar wind be responsible for periodically dispersing the dust, making the clouds shrink or shift position? Or does it push new particles into the Lagrange points, replenishing them? If this is the case, then the Kordylewski Clouds might serve as an indicator of solar activity. If their density changes in response to fluctuations in the solar wind, then studying them could provide new insights into how our sun influences dust movement in space. This would be particularly useful for understanding how dust behaves not just around Earth, but throughout the entire solar system. And if the Kordylewski Clouds are linked to solar activity, could they also be affected by Earth's own atmospheric processes? Some scientists have speculated that powerful geomagnetic storms, caused by interactions between the solar wind and Earth's magnetic field, might influence the behavior of dust in near-Earth space. If so, the Kordylewski Clouds could be indirectly shaped by Earth itself, making them a unique phenomenon where planetary, solar, and interstellar forces all converge. The possibility that these clouds could be part of a much larger, hidden dust structure around Earth is even more fascinating. What if they are simply the most visible regions of a nearly invisible dust ring encircling our planet? Some scientists have proposed that Earth, like Saturn or Jupiter, might have a faint dust ring that has gone undetected for centuries. This ring would be composed of particles that accumulate due to gravitational interactions, solar radiation, and lunar activity. If such a structure exists, then the Kordylewski Clouds might be the densest portions of this ring, acting as gravitational traps where dust settles and lingers. If this is true, then it completely changes our understanding of Earth's near-space environment. We often think of space around our planet as mostly empty, but what if it's actually filled with delicate, ever-shifting clouds of dust? If this dust ring exists, it could have a subtle but significant impact on space exploration. Could it affect the orbits of satellites? Could it pose a risk to spacecraft traveling through it? Could it even play a role in Earth's atmospheric patterns in ways we have yet to understand? And then there's the question of what kind of material makes up the Kordylewski Clouds. We know that they are composed of fine dust particles, but where did this dust come from? One theory is that the particles originated from the Moon, ejected into space by impacts from micrometeorites. If this is the case, then the Kordylewski Clouds could contain ancient lunar material, effectively making them floating reservoirs of moon dust suspended in Earth's orbit. If we were to send a spacecraft to collect samples from these clouds, we might find particles that date back millions, or even billions, of years. These particles could hold clues about the history of the Moon, revealing details about its past surface conditions and impact events. Some of the dust might even come from beyond our solar system, making the Kordylewski Clouds a potential repository of interstellar material that has drifted into our cosmic neighborhood over time. This raises the possibility that the Kordylewski Clouds could be more than just a passive accumulation of dust. They could be a time capsule. If they have been stable for millions of years, then they might contain preserved particles from ancient cosmic events. Traces of long-gone comets, remnants of distant supernova explosions, or even interstellar grains from deep space might be hidden within them. Studying these clouds could provide a rare opportunity to analyze the history of dust movement in the solar system, revealing how cosmic material has traveled and interacted with planets over vast stretches of time. Another fascinating aspect of the Kordylewski clouds is the way they interact with light. Because they are composed of tiny, dispersed particles, they scatter light in unusual ways. Some researchers have suggested that, under the right conditions, these clouds could create subtle optical effects in the night sky. They might appear as faint, glowing patches of light, similar to the zodiacal light, the soft glow that comes from interplanetary dust-scattering sunlight. If the Kordylewski clouds do produce visible light effects, then they could represent a new type of atmospheric or space-based optical phenomenon that has been overlooked for centuries. Observers throughout history might have mistaken them for faint nebulae or unexplained night glows. If astronomers can confirm and map these optical effects, it could provide a new way to detect and study the clouds without needing complex instruments. The idea that these clouds might produce visible light also raises another possibility. What if they can be detected not just in visible wavelengths, but in infrared or even radio frequencies? If the dust particles within the Kordylewski clouds interact with electromagnetic radiation in unexpected ways, they might be detectable using specialized telescopes that scan the sky in different parts of the spectrum. Future studies could involve using infrared and radio telescopes to search for subtle emissions from the Kordylewski clouds. If they do emit in these wavelengths, then we might be able to create detailed maps of their structure, density, and movement over time. This could reveal patterns that are currently invisible to the human eye, helping us understand how these mysterious dust clouds behave in orbit around Earth. One particularly interesting question is whether the Kordylewski clouds could have any effect on Earth's climate. At first glance, it might seem unlikely that two relatively faint clouds of dust, positioned far from the planet, could influence weather patterns or global temperatures. However, some scientists have speculated that even small-scale space dust accumulations could play a role in the planet's energy balance. Dust particles in space can scatter and absorb sunlight, altering the way energy moves through the Earth's atmosphere. If the Kordylewski clouds are dense enough in certain regions, they might slightly reduce the amount of sunlight reaching Earth's surface. Even if the effect is minimal, over long periods of time, it could have cumulative consequences. This concept has been explored in climate models, where even minor changes in sunlight absorption can shift weather patterns in unpredictable ways. Additionally, if the Kordylewski clouds interact with Earth's magnetosphere, its protective magnetic field, then they could influence the movement of charged particles around the planet. The magnetosphere is responsible for shaping space weather, including phenomena like the auroras and radiation belts. If the dust in these clouds carries electric charges, it could create localized disturbances in Earth's magnetic environment. Understanding whether the Kordylewski clouds have any measurable impact on Earth's climate or magnetosphere would require long-term observation and analysis. Scientists would need to track the density of the clouds over many years, correlating any changes with atmospheric and magnetic data from Earth. If a connection were found, it would provide yet another reason why these clouds are far more important than their faint appearance suggests. The implications of studying the Kordylewski clouds go beyond Earth alone. If our planet has accumulated dust clouds at its Lagrange points, then it's reasonable to ask whether other planets in the solar system have similar formations. Could Mars, Venus, or even Jupiter have their own versions of Kordylewski clouds? If so, these dust accumulations might play an unseen role in shaping the environments of other planets. For example, if Mars has dust clouds in its Lagrange points, they could contribute to the movement of fine Martian dust across its atmosphere. On a planet like Jupiter, which has a much stronger gravitational field, such dust clouds might be even denser and more complex than those near Earth. If these formations exist throughout the solar system, then they might be a common but overlooked feature of planetary environments. This also raises questions about the role of Lagrange points in the broader context of space exploration. Scientists and engineers have long considered these stable points in space as potential locations for space stations, telescopes, and even future human habitats. If dust clouds like the Kordylewski clouds exist at these points, then any future missions would need to take them into account. For instance, if we were to place a space station at the L4 or L5 points, how would the presence of dust affect its operations? Would the constant movement of fine particles pose a risk to sensitive instruments? Would spacecraft traveling to these locations need special shielding to protect against long-term exposure to the dust? These are all practical considerations that would need to be addressed before humans could permanently occupy these regions of space. And what about the potential for using these clouds as a resource? If they are composed of lunar dust or interstellar material, could they be mined or studied in detail to extract valuable information? Future space missions could be designed to capture and analyze the dust particles within the Kordylewski Clouds, potentially providing insights into both the history of our own solar system and the nature of dust in interstellar space. One of the most fascinating aspects of the Kordylewski Clouds is how little we still know about them. Despite being theorized for nearly a century and observed in recent years, they remain a largely unexplored phenomenon. Many fundamental questions remain unanswered. How stable are they over time? How much dust do they actually contain? What are the precise sources of this dust? And could there be more undiscovered structures in Earth's orbit that we have yet to detect? This is why continued observation and research into these clouds are so important. With advances in space telescopes, Earth-based observatories, and even potential future space probes, we may soon uncover more details about the true nature of the Kordylewski Clouds. They might be a minor curiosity in the grand scheme of the cosmos, or they might turn out to be far more significant than we ever imagined. What's certain is that they represent another reminder that space is full of mysteries, even in regions as close to us as our own planetary orbit. The more we study these enigmatic dust clouds, the more we may come to understand not just the nature of dust in space, but the complex interactions between Earth, the Moon, the Sun, and the unseen forces that shape our solar system. And if we've only recently confirmed the existence of the Kordylewski Clouds, what else is out there, hiding just beyond our perception, waiting to be discovered? The mystery of the Kordylewski Clouds is a reminder that even in the regions of space we think we understand, there are still hidden phenomena waiting to be explored. If such elusive structures exist near Earth, what else could be lurking in the vastness of our solar system? Could there be similar dust clouds at Lagrange points around other planets? And if so, what role might they play in shaping planetary environments? The idea that these clouds might exist elsewhere is more than just speculation. The conditions that allow them to form near Earth, stable gravitational points, the presence of interplanetary dust, and interactions with solar radiation, also exist around other celestial bodies. Jupiter, for example, has an extensive system of Lagrange points where its massive gravity creates regions of stability. These regions already host thousands of Trojan asteroids, but could there also be dust clouds similar to the Kordylewski Clouds? If such clouds exist, they might provide crucial insights into how dust behaves in different planetary systems. Dust is a fundamental component of the universe, playing a key role in star formation, planetary accretion, and even the chemistry of interstellar space. Understanding how it gathers and moves within a solar system could help answer deeper questions about planetary evolution. One of the most intriguing possibilities is that the Kordylewski Clouds might contain traces of material from beyond our solar system. Space dust isn't just made up of particles from the Moon or remnants of asteroids. Some of it comes from interstellar space, carried into our solar system by cosmic currents. If the Kordylewski Clouds act as a kind of gravitational trap, then they might hold tiny samples of material that originated from distant stars, offering a rare opportunity to study interstellar dust without needing to leave Earth's vicinity. This leads to another question: could the Kordylewski Clouds serve as a natural archive of cosmic history? If they have been stable for thousands, or even millions, of years, they might contain preserved dust grains from ancient supernovae, comets that passed through the solar system long ago, or even the primordial material that formed Earth and the Moon. Studying these particles could reveal information about the early solar system, the formation of planets, and the types of cosmic events that have influenced Earth over time. The challenge, of course, is collecting samples from the clouds. Unlike the Moon, which has a solid surface that astronauts can land on, the Kordylewski Clouds are diffuse and constantly shifting. Capturing material from them would require highly sensitive spacecraft capable of filtering and analyzing tiny dust particles in microgravity. Such a mission could be designed to fly through the densest regions of the clouds, collecting samples and returning them to Earth for detailed study. But before we send spacecraft to investigate, there's still much we need to learn from Earth. Ground-based telescopes and space observatories will continue to monitor the clouds, tracking their movement and composition. Advances in optical technology may allow us to get clearer images, revealing whether the clouds have distinct structures or patterns that change over time. Another intriguing possibility is that the Kordylewski clouds might interact with Earth's atmosphere in ways we haven't yet detected. If particles from these clouds occasionally drift toward Earth, could they contribute to meteor showers or influence the density of our upper atmosphere? It's a possibility worth exploring, especially as we continue to study the complex relationship between Earth and its space environment. And then there's the question of whether similar dust clouds exist around other stars. If Kordylewski-like clouds are a natural consequence of planetary systems, then exoplanets in other star systems might have their own versions of these mysterious formations. Observing these dust clouds from a distance could provide indirect clues about the presence of planets, moons, or asteroid belts around distant stars. This idea ties into the broader search for habitable planets beyond our solar system. If dust clouds exist around exoplanets, they could help scientists infer details about the planet's atmosphere, magnetic field, and even the potential for life. Some researchers have proposed that dust clouds could act as shields, protecting planets from excessive solar radiation. If this is true, then the presence of such clouds around an exoplanet might make it a more promising candidate for habitability. The study of the Kordylewski clouds is still in its early stages, but their discovery has already opened up a new frontier in space research. They challenge our understanding of how dust behaves in space, raise questions about the long-term stability of Lagrange points, and hint at the possibility of undiscovered structures lurking in our own cosmic backyard. And as we continue to explore, we must ask ourselves, what else are we missing? If something as significant as these dust clouds remained hidden for so long, what other mysteries of space are waiting to be uncovered? The discovery of the Kordylewski clouds raises profound questions about what else might be hiding in the depths of our solar system. If these massive dust clouds, orbiting relatively close to Earth, remained undetected for so long, then it stands to reason that even more elusive phenomena could be waiting to be found. Could similar clouds exist at other Lagrange points, not just around Earth, but around Mars, Venus, or even the gas giants like Jupiter and Saturn? If they do, what role might they play in shaping the evolution of planetary systems? One of the most fascinating aspects of these clouds is their potential to serve as natural collectors of interstellar material. Space dust travels across vast cosmic distances, carrying with it the chemical signatures of dying stars, supernova explosions, and even the primordial dust that existed before the solar system was formed. If the Kordylewski clouds act as a gravitational trap for such material, they could hold microscopic particles that have traveled through space for billions of years. Studying these particles could provide insights into the very origins of the universe itself. Another important aspect to consider is the way these clouds interact with cosmic radiation. Space is filled with high-energy particles, including those from the Sun and distant astrophysical events. Some researchers speculate that the Kordylewski clouds might play a role in filtering or scattering this radiation, subtly influencing the space environment around Earth. If true, this could have implications for understanding how cosmic radiation interacts with planetary atmospheres and even how it affects life on Earth. It's also worth considering whether the Kordylewski clouds could be part of a larger, yet undiscovered network of dust structures orbiting Earth. The solar system is filled with dust from countless sources: comets shedding material as they approach the Sun, asteroid collisions producing debris, and interstellar dust drifting into our system from deep space. Could it be that these clouds are just one piece of a much larger and more complex web of cosmic dust formations? If so, this could have major implications for future space exploration. As humanity sets its sights on long-term space travel, whether to the Moon, Mars, or beyond, understanding the distribution of dust in space becomes increasingly important. Spacecraft traveling through these regions will need to navigate through areas of varying dust density, and long-term exposure to these particles could pose risks to both equipment and human explorers. Some scientists have even proposed that large dust clouds, like the Kordylewski Clouds, might play a role in the development of planetary rings. Saturn's rings, for example, are composed primarily of ice particles, but what if there were once structures similar to the Kordylewski Clouds in orbit around Earth or other planets? Could some of them have eventually coalesced into rings or moons? Understanding the stability and behavior of dust clouds could help answer these questions and provide clues about how planetary systems evolve over time. Another possibility worth exploring is whether these dust clouds could serve as waypoints or fuel sources for future spacecraft. While it may seem far-fetched, some proposed space missions involve using solar sails, thin, reflective materials that harness the pressure of sunlight to propel a spacecraft forward. If dust clouds like the Kordylewski Clouds are dense enough in certain areas, they might provide a medium for experimental propulsion systems that interact with fine particles in space. Additionally, the study of these clouds could help refine our models of space weather. The movement of charged particles, interactions between dust and electromagnetic fields, and the scattering of light by fine particles all contribute to the complex and dynamic environment of near-Earth space. By studying how the Kordylewski Clouds shift and change over time, we could improve our ability to predict and model space weather events that impact satellites, communications, and even power grids on Earth. Ultimately, the Kordylewski Clouds serve as a reminder that even in our own cosmic neighborhood, mysteries abound. Their existence challenges our understanding of gravitational dynamics, space dust behavior, and the interactions between celestial bodies. They also highlight the fact that our exploration of space is still in its infancy. There is so much left to discover, even within the confines of our solar system. As technology advances and our ability to observe faint, diffuse structures improves, we may find that the Kordylewski Clouds are just the beginning. They could be the first of many hidden features of our space environment, waiting to be uncovered by future generations of scientists, astronomers, and explorers. What other secrets are waiting to be revealed? Only time, and continued exploration, will tell. The Kordylewski Clouds, while largely unknown to the general public, represent a fascinating puzzle that challenges our understanding of how dust behaves in space. Unlike the well-defined rings of Saturn or the dramatic tails of comets, these clouds are subtle, nearly invisible formations, only detectable under the right conditions. But if they exist as stable structures, it raises even bigger questions. Could they have existed for millions of years? And if so, how might they have influenced Earth's history in ways we haven't even considered? One of the most interesting possibilities is that the Kordylewski Clouds might have played a role in shaping Earth's climate. Dust in space can have surprising effects on planetary atmospheres. For example, interplanetary dust that drifts into Earth's atmosphere contributes to noctilucent clouds, high-altitude clouds that glow in the twilight sky. If the Kordylewski Clouds occasionally release dust into Earth's atmosphere, they could be influencing weather patterns in ways that remain undetected. Some researchers have even speculated about a connection between cosmic dust and climate shifts on a much larger scale. Could periods of increased dust accumulation from space contribute to global cooling events? There is some evidence that Earth has gone through cycles of increased dust deposition, which might have affected temperatures over long timescales. If the Kordylewski Clouds are denser at certain points in their orbit, they might occasionally contribute more dust to Earth's environment, subtly altering the amount of sunlight that reaches the surface. This idea ties into a broader question in planetary science. How much influence does space dust have on habitability? We tend to think of Earth's atmosphere as a closed system, where climate is controlled by ocean currents, greenhouse gases, and solar activity. But what if a hidden factor, like the gradual accumulation of interplanetary dust, has been playing a role all along? The Kordylewski Clouds might provide a natural test case for studying this interaction, offering a unique opportunity to understand how dust in space can shape the conditions of a planet over time. Beyond climate effects, there is another fascinating possibility. Could the Kordylewski Clouds be a potential source of organic molecules? Space dust is not just composed of lifeless rock and ice. It often contains complex organic compounds, including the building blocks of life. Some theories of abiogenesis, the origin of life, propose that essential molecules for life may have been delivered to Earth by comets, asteroids, or interstellar dust. If the Kordylewski Clouds contain a steady supply of organic-rich material, they could be part of a much larger cosmic cycle, continuously replenishing Earth's environment with essential molecules. This raises an even deeper question. Could dust clouds like these play a role in seeding life elsewhere in the universe? If Kordylewski-like clouds exist around other planets, they might serve as a delivery system for organic molecules, increasing the chances that life could emerge under the right conditions. If we one day find similar dust clouds orbiting exoplanets, they could be an important clue in the search for extraterrestrial life. Another avenue of research involves the potential impact of these clouds on space travel. As humanity pushes further into space, long-term missions will need to account for potential hazards, including cosmic dust. If the Kordylewski clouds are denser than we realize, they could pose challenges for spacecraft traveling through the Lagrange points. Tiny dust particles might seem insignificant, but at high velocities, they can be dangerous, eroding surfaces, damaging sensors, and even posing a risk to astronauts. Understanding the density and movement of these clouds is crucial for planning safe navigation routes for future missions. At the same time, the Kordylewski clouds might also offer unexpected opportunities for space exploration. If they contain a high concentration of useful materials, such as water ice, carbon compounds, or even rare metals, they could serve as a potential resource for future space mining operations. While it may seem like science fiction, the idea of harvesting materials from space is already being considered for asteroids and the Moon. If the Kordylewski clouds turn out to be a stable and accessible source of valuable elements, they might become a key target for space industry in the future. This brings us to another important question: how stable are the Kordylewski clouds over time? If they have existed for millions of years, it suggests that dust can persist in stable regions of space far longer than previously thought. But if they are constantly shifting and reforming, it might indicate that these structures are more dynamic than we realize. By studying their long-term behavior, we could learn more about how dust moves throughout the solar system and even how similar structures might exist around other celestial bodies. Despite their elusive nature, the Kordylewski clouds challenge us to rethink our assumptions about what exists in the space around us. For centuries, scientists have believed that Earth's immediate surroundings were relatively empty, aside from the Moon and artificial satellites. The existence of these vast, yet nearly invisible dust clouds suggests otherwise. It serves as a humbling reminder that even in the regions we think we know best, there are still mysteries waiting to be uncovered. The more we learn about the Kordylewski clouds, the more questions arise. Could they be part of a much larger, yet undiscovered structure in our solar system? Do they interact with Earth's magnetic field in unexpected ways? And could they hold the key to understanding other, more distant dust clouds that might be orbiting exoplanets? The answers to these questions may take years, or even decades, to uncover. But one thing is certain: the Kordylewski clouds have opened a new chapter in our exploration of space, reminding us that even in our own cosmic backyard, there is still so much left to discover. The Kordylewski clouds may be some of the most overlooked yet fascinating structures in our cosmic neighborhood. For decades, their existence was debated, dismissed, and often ignored due to their elusive nature. But if these dust clouds have been orbiting Earth for centuries, what else could be hiding in the shadows of space, waiting to be discovered? One of the most intriguing aspects of these clouds is their relationship with Earth's gravitational environment. The Lagrange points where they reside, specifically L4 and L5, are known for their stability, but that doesn't mean these clouds are entirely stationary. They may be shifting, evolving, and even dispersing over time, forming and reforming as they interact with solar wind, cosmic radiation, and Earth's own magnetosphere. If that's the case, then they aren't just static dust clouds, they're dynamic, ever-changing structures that could offer insights into how interplanetary matter behaves over long periods. The possibility of their movement also raises the question of whether they leave a subtle but measurable impact on Earth. Could the slow drift of dust from these clouds create periodic changes in our planet's upper atmosphere? Some scientists believe that space dust plays a small but significant role in atmospheric chemistry. For example, when micrometeoroids enter Earth's atmosphere, They burn up and deposit elements like iron, magnesium, and silicon. Over long timescales, even a small increase in dust accumulation could subtly influence the composition of our atmosphere. But what if the Kordylewski clouds do more than just contribute dust? Could they act as a kind of natural filter, capturing interstellar particles as they drift through our solar system? If so, these clouds might be an untapped resource for studying materials from beyond our solar system. By analyzing their composition, scientists might find evidence of exotic elements, isotopes, or even interstellar compounds that could offer clues about the environments they originated from. This leads to another major question: could similar clouds exist around other planets? If Earth has massive dust clouds at its stable Lagrange points, then there's a good chance that Mars, Venus, and even gas giants like Jupiter and Saturn have them too. If confirmed, it would change our understanding of how dust circulates in planetary systems. These structures might be far more common than we ever realized, and if they contain organic compounds, they could even contribute to the development of life in ways we haven't yet imagined. Speaking of organic compounds, some theories suggest that dust clouds like these could play a role in the transfer of life between planets, a concept known as panspermia. If the Kordylewski clouds contain organic molecules, they might act as a temporary storage system, trapping biological material ejected from Earth or elsewhere in the solar system. If this material eventually drifts toward another planet, it could introduce the building blocks of life to an entirely new environment. Could this mean that Kordylewski-like clouds exist around exoplanets as well? If we find similar dust structures in other solar systems, they could serve as indicators of planetary habitability. Astronomers searching for life-friendly exoplanets typically look for atmospheres with certain chemical signatures. But what if we also need to consider the presence of dust clouds that might be distributing organic material? The implications could be enormous, as it would suggest that dust plays a bigger role in the cosmic cycle of life than we previously believed. On a more practical level, the existence of these clouds could also influence future space missions. If they contain significant amounts of fine dust, they could pose a risk to spacecraft passing through L4 and L5. Tiny dust grains traveling at high speeds could damage spacecraft surfaces, interfere with sensors, or even pose a threat to astronauts on long-term missions. Understanding the density and behavior of these clouds will be crucial as space agencies plan future lunar and deep space missions. At the same time, they might also provide opportunities. If these clouds contain materials useful for space travel, such as carbon compounds or water ice, they could serve as potential waypoints for spacecraft in the future. Instead of carrying all necessary resources from Earth, future missions could extract valuable materials from naturally occurring dust clouds. This concept, known as in situ resource utilization, is already being explored for the Moon and asteroids, but the Kordylewski clouds could represent an entirely new category of space resources. Another key mystery surrounding these clouds is how they interact with electromagnetic radiation. Unlike solid celestial bodies, which block or reflect light in predictable ways, dust clouds scatter and absorb light in complex patterns. This makes them difficult to observe with traditional telescopes, but it also means they could have unexpected optical effects. Some scientists have speculated that under the right conditions, the Kordylewski clouds might contribute to subtle optical phenomena in the night sky, faint glows, unusual patterns of scattered light, or even unexplained fluctuations in brightness detected by sensitive instruments. If this turns out to be true, it could have implications for astronomy as a whole. When astronomers observe distant stars, galaxies, and exoplanets, they rely on precise measurements of light. But if structures like the Kordylewski clouds exist around multiple planets, they could introduce a new source of interference, one that we haven't yet accounted for. Understanding how these clouds scatter light could help refine observational techniques and improve the accuracy of future astronomical studies. In the grand scheme of things, the Kordylewski clouds serve as a reminder of how much we still have to learn about our own cosmic backyard. They challenge the assumption that space near Earth is empty, revealing instead that complex, dynamic structures can exist in places we once thought were voids. They also highlight the importance of continued observation, Because if we could overlook something as large as these dust clouds for so long, what else might be lurking undetected in our solar system? Perhaps the biggest takeaway from the study of the Kordylewski clouds is that they reinforce the need for curiosity. Science is at its best when it questions assumptions, challenges conventional wisdom, and pushes the boundaries of what we know. The fact that these clouds were dismissed for decades, only to be confirmed much later, shows that sometimes, the most interesting discoveries come from ideas that were once considered impossible. What else might be hiding in the space around us? Are there other, even larger dust structures orbiting Earth that we haven't yet detected? Could there be additional hidden objects, asteroids, frozen debris, or unknown phenomena, lingering in gravitationally stable regions near our planet? The more we investigate, the more we realize that space, even in our immediate vicinity, is far from empty. It is filled with complexities, mysteries, and phenomena that continue to surprise us. And so, the study of the Kordylewski clouds is just the beginning. As technology improves and observational techniques become more refined, we may uncover even more hidden structures in the space around Earth. Each new discovery will bring with it new questions, new theories, and new possibilities. Because if we've learned anything from the history of space exploration, it's that the universe is always more mysterious than we expect. The mysteries surrounding the Kordylewski clouds raise an even bigger question. How many other cosmic structures have gone unnoticed simply because we haven't been looking for them in the right way? The discovery of exoplanets, dark matter, and even the cosmic microwave background all came from shifting our perspective and improving our observational tools. If these massive dust clouds could remain hidden for so long, it's possible that other celestial structures, perhaps even stranger ones, are lurking just beyond our current understanding. One of the most intriguing aspects of the Kordylewski clouds is their potential connection to the broader field of planetary dust dynamics. We already know that dust plays a major role in shaping planetary systems, from the early stages of planet formation to the distribution of interplanetary debris. Could the study of these clouds help us unlock new insights into how planets and moons interact with dust in their orbits? For instance, some astronomers speculate that similar clouds may exist around Mars, Venus, or even Saturn's moons. If these clouds are more common than we think, they could provide clues about how dust accumulates in certain regions of space and how it might influence planetary evolution. The stability of dust in Lagrange points could also have implications for understanding planetary rings, asteroid belts, and even the behavior of dust in protoplanetary disks, when new planets are born. The possibility of hidden dust structures also has implications for space exploration. Space agencies like NASA and ESA are constantly looking for regions of space that may pose risks to satellites, space stations, and future crewed missions. If large-scale dust clouds exist near key orbital locations, they could represent navigational hazards that need to be accounted for. Even small, millimeter-sized dust particles can damage spacecraft traveling at high speeds, so mapping out these clouds with greater precision could become a priority for mission planners. But what if we could turn the Kordylewski clouds into an asset instead of a risk? Some researchers have proposed that dust clouds like these could act as natural shields against cosmic radiation. Spacecraft traveling beyond Earth's protective magnetic field are exposed to dangerous levels of radiation from the sun and cosmic rays. If the Kordylewski clouds contain enough material to absorb some of this radiation, they could potentially be used as staging points for long-duration space missions. This idea ties into the broader concept of space resource utilization. If we could harness the dust from these clouds, it might serve as raw material for 3D printing in space, creating structures or even protective barriers for astronauts. Some experts have suggested that lunar dust could be used for similar purposes, so why not consider the Kordylewski clouds as another potential resource? If future technology allows us to capture and manipulate space dust efficiently, these clouds could become a valuable supply depot in orbit. Then there's the question of how the Kordylewski clouds formed in the first place. While some theories suggest that they are simply accumulations of dust caught in Earth's gravitational pull, others propose more exotic origins. Could they be remnants of an ancient cosmic event? Perhaps the debris from a long-lost asteroid collision, or even the remains of a small moon that disintegrated over millions of years? If these clouds are composed of material not commonly found in Earth's vicinity, it could hint at an unexpected origin story, one that might even involve interstellar dust or remnants from the early solar system. To solve these mysteries, scientists will need better observational tools. Current methods for studying the Kordylewski clouds rely heavily on indirect measurements, such as analyzing how light scatters off the dust particles. But new advances in space-based telescopes and imaging technology could allow us to capture higher-resolution data. Future lunar missions might even place dedicated instruments at L4 and L5 to study these clouds up close, providing direct measurements of their composition, density, and behavior. And speaking of behavior, another pressing question is whether these clouds are truly stable over long timescales. Some models suggest that the dust within them is constantly shifting, influenced by solar wind, lunar gravity, and other cosmic forces. If this is the case, then the Kordylewski clouds might not be permanent structures but rather transient features that form, dissipate, and reform over time. If so, understanding their life cycle could provide insights into similar dust formations across the galaxy. Could there be an entire network of dust clouds hidden in gravitationally stable zones throughout the solar system? If the Kordylewski clouds are just one example, then we may have vastly underestimated the role of dust in shaping planetary environments. These clouds might not just be passive accumulations of particles, they could be dynamic systems that influence space weather, planetary magnetospheres, and even the potential spread of organic material across space. The implications extend far beyond Earth. If other planets in our solar system have similar dust clouds, they could impact everything from planetary atmospheres to the feasibility of future missions. For example, if Mars has Kordylewski-like clouds, they could affect how dust storms form on the planet, or even alter the effectiveness of solar-powered landers. Understanding how dust behaves in space is crucial, and the Kordylewski clouds offer a unique opportunity to study this phenomenon right in our cosmic backyard. Ultimately, the discovery of these clouds reminds us that space is anything but empty. Even in regions we once thought were devoid of significant structures, new surprises continue to emerge. The fact that these dust clouds were first proposed decades ago but only recently confirmed highlights the importance of keeping an open mind in scientific exploration. What other mysteries are waiting to be uncovered? If the Kordylewski clouds have been orbiting Earth all this time without us fully realizing it, what else might be hidden in the cosmic shadows? Could there be undiscovered objects, gravitational anomalies, or even entirely new types of celestial structures that challenge our understanding of space? Science thrives on curiosity, and the study of the Kordylewski clouds is just one example of how seemingly small discoveries can lead to big questions. As we continue to explore space, refine our observational techniques, and push the boundaries of what we know, we may find that the universe is far more complex, and far more mysterious, than we ever imagined. The realization that space is filled with more hidden structures than we ever anticipated forces us to rethink our assumptions about the universe. The Kordylewski clouds may seem like mere accumulations of dust, but they represent something much greater, a reminder that our cosmic neighborhood is still full of surprises. The fact that these clouds exist at all challenges our perception of the Earth-Moon system as a relatively well-understood domain. If such massive, yet elusive, structures can persist in gravitational equilibrium, what else might be lurking in similar stable zones across the solar system? This brings us to the idea that other celestial bodies may have their own versions of the Kordylewski clouds. Jupiter, for instance, has an extensive system of moons, and its Lagrange points are known to harbor Trojan asteroids, objects that share the planet's orbit in these gravitationally stable regions. But could Jupiter also have vast dust clouds swirling in its own L4 and L5 points, hidden from direct observation? If so, these could provide clues about how planetary systems manage and redistribute debris over billions of years. Beyond Jupiter, the same logic applies to Saturn, Neptune, and even exoplanetary systems. In fact, if we start actively looking for dust clouds at Lagrange points around other planets, we might find that they are a common feature rather than a rarity. Studying them could help us understand how planetary dust interacts with gravitational forces, magnetic fields, and solar wind, phenomena that play a crucial role in shaping both planetary and interstellar environments. The study of cosmic dust itself has gained increasing attention in recent years. Dust is not just a nuisance that coats telescopes or interferes with spacecraft, it is a fundamental ingredient of the universe. Interstellar dust carries the raw materials for planet formation, and some theories even suggest that dust particles may have played a role in seeding life on Earth by carrying complex organic molecules across space. If the Kordylewski Clouds contain unique or unexpected elements, they might provide evidence for these theories. Could these clouds be acting as reservoirs of ancient cosmic material, holding particles that predate the formation of the Earth? This possibility raises another intriguing question. What if similar dust clouds existed in the early solar system, playing a role in the formation of Earth itself? If massive accumulations of dust at Lagrange points were present billions of years ago, they could have influenced how material coalesced into planets and moons. Some planetary formation models suggest that Lagrange points may have temporarily trapped large amounts of debris, allowing material to clump together before eventually merging with a growing planetary body. If this idea holds true, then the Kordylewski Clouds might not just be a present-day curiosity. They could be remnants of a much older process, providing a rare glimpse into the early history of our solar system. Future missions equipped with dust analyzers could determine the exact composition of these clouds, potentially revealing whether they contain primordial material that has remained relatively unchanged for eons. Another compelling angle to explore is the potential connection between the Kordylewski Clouds and space weather. We know that solar activity, including coronal mass ejections and high-energy cosmic rays, can have significant effects on Earth's atmosphere and magnetosphere. But how do these energetic forces interact with the delicate particles within the Kordylewski Clouds? Could the clouds act as a kind of cosmic buffer, absorbing some of this incoming energy and dispersing it in unpredictable ways? If the Kordylewski Clouds do influence space weather, this could have major implications for both satellite operations and human spaceflight. Engineers already have to account for the risks posed by space dust and micrometeoroids when designing spacecraft. If the Kordylewski Clouds contain a denser-than-expected concentration of particles, they might pose additional challenges for future lunar missions or even space tourism ventures. Understanding their behavior could be crucial for planning long-duration space travel, ensuring that spacecraft can navigate safely through these potentially hazardous regions. Then there's the possibility that the Kordylewski Clouds could play a role in Earth's own atmospheric and climate systems. Some researchers have speculated that large-scale dust clouds in space might contribute to faint optical effects in the sky, influencing the way sunlight is scattered or even affecting nocturnal brightness levels. Could these clouds be responsible for subtle variations in how we perceive the night sky? Could they be part of a larger, yet-to-be-discovered system of interplanetary dust that subtly alters Earth's environmental conditions? To answer these questions, more advanced observational methods will be necessary. While recent studies have provided strong evidence for the existence of the Kordylewski Clouds, we are still in the early stages of fully understanding them. The next step will likely involve sending dedicated probes or deploying telescopes specifically designed to analyze the clouds in unprecedented detail. Such missions could map their structure, measure their density, and even capture direct samples of the dust particles for laboratory analysis. If humanity ever establishes a permanent presence on the Moon, the Kordylewski Clouds could become an important factor in lunar operations. The L4 and L5 points, where the clouds reside, are prime locations for future space stations or refueling depots. If these regions are filled with dust, engineers and mission planners will need to develop strategies to mitigate any potential risks. Alternatively, if the clouds contain useful materials, they could be harvested as part of in-situ resource utilization efforts. As we continue to push the boundaries of space exploration, seemingly minor discoveries like the Kordylewski Clouds remind us that the universe is still full of unknowns. Every new observation opens the door to more questions, forcing us to rethink what we thought we knew about planetary systems, cosmic dust, and the hidden forces that shape our solar neighborhood. What else is hiding in plain sight, waiting for the right observer to uncover it? Could there be other dust formations, gravitational anomalies, or unexpected cosmic structures that we have overlooked simply because we weren't looking in the right way? The history of space exploration is full of paradigm shifts, moments where something previously dismissed as insignificant turned out to hold profound scientific value. The Kordylewski Clouds may be just the beginning. If we start actively searching for similar structures across the solar system and beyond, who knows what we might find? Perhaps there are entire networks of dust clouds influencing planetary evolution, shaping the destinies of worlds in ways we have yet to comprehend. As new telescopes come online, as spacecraft venture deeper into space, and as our understanding of cosmic phenomena continues to expand, we may look back on the discovery of the Kordylewski Clouds as one of the first steps in unraveling an even greater mystery. The more we think about it, the clearer it becomes that the Kordylewski Clouds might not be some isolated anomaly but part of a larger, more intricate cosmic framework. They could be a mere fragment of a broader, yet undiscovered network of dust structures that exist in the gravitationally stable regions of planetary systems. If similar dust formations exist in other Lagrange points around Earth, or even around other planets, it could redefine how we understand the movement of dust and debris within solar systems. One of the biggest mysteries surrounding the Kordylewski Clouds is their persistence. Space is dynamic. Dust particles, especially tiny ones, don't just stay in place forever. Solar wind, radiation pressure, and gravitational perturbations constantly push and pull at them. And yet, despite these forces, these clouds appear to have remained in roughly the same locations for decades, if not centuries. How is that possible? What mechanisms are at play that allow such an ephemeral structure to endure for so long? One possibility is that the dust within the clouds is constantly being replenished. But where is this dust coming from? Some researchers have speculated that micrometeoroid impacts on the Moon could be a significant source. Every day, tiny meteoroids collide with the lunar surface, kicking up clouds of dust that could slowly migrate to the L4 and L5 points. If this process has been ongoing for billions of years, it might explain why the Kordylewski Clouds are still present today. But that's not the only explanation. Some theories suggest that the dust could be remnants of ancient interplanetary material, possibly even debris left over from the formation of the Earth-Moon system itself. If that's the case, then these clouds might not just be a curiosity. They could be a scientific goldmine, preserving ancient material from the earliest days of our solar system. If we were to send a spacecraft to collect samples from the Kordylewski Clouds, we might gain direct insight into the conditions that existed billions of years ago. What if these particles contain rare isotopes, organic compounds, or even clues about the chemistry of preplanetary dust? Could they provide hints about the building blocks that eventually led to the formation of planets, moons, and maybe even life itself? And then there's the question of what role these clouds might play in our own planetary environment. We often think of Earth's atmosphere as a self-contained system, influenced mainly by solar radiation, volcanic activity, and human industry. But what if interplanetary dust, especially structures like the Kordylewski Clouds, also plays a subtle but important role? For example, could these dust clouds affect Earth's climate? We already know that fine particles in the upper atmosphere can influence weather patterns and even contribute to global cooling by reflecting sunlight. If the Kordylewski Clouds occasionally shed dust that drifts toward Earth, could it have a similar effect? Some researchers have speculated that during periods of increased solar activity, more dust might be knocked loose from these clouds, potentially leading to tiny but measurable impacts on Earth's atmosphere. It's also possible that these clouds interact with Earth's magnetosphere in ways we don't yet fully understand. The magnetosphere is our planet's protective shield, deflecting charged particles from the solar wind and cosmic rays. If a significant amount of dust exists in the L4 and L5 points, it could influence how these charged particles move through space, potentially affecting phenomena like auroras, radio signal propagation, or even the behavior of satellites in Earth's orbit. Another mystery is whether the Kordylewski Clouds could pose a potential hazard for future space missions. Right now, our spacecraft don't generally pass through the L4 and L5 points, so we don't have to worry much about colliding with dust particles. But as humanity expands its reach into space, Especially with planned lunar bases and deep space missions, these clouds could become more relevant. If the dust is denser than expected, it could pose a risk to spacecraft, damaging sensitive instruments or eroding surfaces over time. Alternatively, the Kordylewski clouds could turn out to be a valuable resource. Some researchers have proposed that space dust could be collected and processed to extract useful elements, such as oxygen or silicon. If the Kordylewski clouds contain significant amounts of such materials, they could serve as a natural reservoir for future space exploration efforts. Imagine a scenario where a lunar outpost or space station taps into these clouds as a source of raw materials, reducing the need to transport supplies from Earth. The implications of these clouds stretch even beyond our own solar system. If similar structures exist around exoplanets, they could provide new ways of studying distant worlds. Astronomers already look for circumstellar dust disks to learn about planet formation, but what if exoplanets also have stable dust clouds at their Lagrange points? Observing such clouds could reveal important details about the composition and dynamics of alien planetary systems. Ultimately, the Kordylewski clouds serve as a powerful reminder that space isn't empty. Even in the seemingly void regions between planets and moons, there are structures waiting to be discovered, structures that can challenge our assumptions and expand our understanding of the universe. If something as large as the Kordylewski clouds can go unnoticed for so long, what else might we be missing? As technology advances and space exploration continues to accelerate, we may find that the universe is far more structured than we ever imagined. Perhaps dust clouds like these exist all over the solar system, forming hidden pathways of interplanetary material. Maybe they act as cosmic archives, preserving the history of planetary formation in ways we have yet to decipher. Or perhaps they are just one piece of an even greater puzzle, one that will take decades, if not centuries, to fully solve. One thing is certain: the more we learn about the Kordylewski clouds, the more questions arise. And that's the essence of science. Every answer leads to new mysteries, new possibilities, and new frontiers to explore. If these clouds have remained hidden for so long, what other cosmic secrets are waiting to be uncovered? The deeper we dig into the mystery of the Kordylewski clouds, the more it becomes clear that these strange dust formations are more than just a fleeting curiosity. They may be an essential part of a vast, hidden system that governs how dust, debris, and even energy move through space. But despite all the speculation, we still lack definitive answers. We don't know exactly how dense these clouds are, how long they've existed, or even whether they are truly stable over time. Could they suddenly dissipate? Or have they been reforming and vanishing on cycles longer than we've been observing them? One of the biggest questions scientists are still trying to answer is whether these clouds are unique to Earth or if they are a universal feature of planetary systems. If other planets in our solar system have Lagrange points, which they do, then could they also have similar dust clouds? If so, we might be looking at a common, yet largely unnoticed, feature of celestial mechanics. Imagine if Mars, Venus, or even Jupiter's moons had their own versions of the Kordylewski clouds, structures that could provide insight into how dust interacts with gravitational forces on a cosmic scale. But if these clouds exist elsewhere, why haven't we detected them around other planets? Perhaps the answer lies in their composition. Unlike planetary rings, which are made up of larger particles that reflect light clearly, the Kordylewski clouds consist of extremely fine dust, making them difficult to observe directly. If similar structures exist around Mars or Jupiter, they may simply be too faint or too diffuse to detect with current instruments. That leads to another possibility. What if the Kordylewski clouds are a stepping stone to understanding something even bigger? We know that interstellar space is filled with dust, but we don't fully understand how it moves or why some regions have more than others. If dust clouds like these exist in planetary systems, could they be part of a larger pattern of cosmic dust migration? Are they remnants of ancient planetary formation processes? Or do they emerge from ongoing interactions between celestial bodies? Another theory suggests that these dust clouds might interact with Earth's gravitational field in unexpected ways. Gravity isn't just a force that pulls objects together, it can create stable zones, like the Lagrange points, where objects can remain in relative equilibrium. If dust is constantly being captured in these zones, could similar processes be occurring on a much larger scale? Could there be hidden dust formations orbiting our solar system at other stable points we have yet to discover? It's also possible that the Kordylewski Clouds are connected to a wider, interplanetary dust cycle that influences everything from asteroid formation to the delivery of organic compounds to planets. We already know that dust plays a critical role in space chemistry. In the vast emptiness between planets and stars, dust grains act as catalysts for chemical reactions, helping form complex molecules, including those necessary for life. If the Kordylewski Clouds serve as reservoirs of dust, could they also be places where new chemical reactions take place? If these clouds are as old as some scientists suspect, they might even hold clues to the early solar system. The dust within them could contain ancient material, unchanged since the time when Earth and the Moon were still forming. That means studying the Kordylewski Clouds isn't just about understanding their current structure. It could also be about unlocking the history of our solar system itself. And then there's the strangest question of all. What if the Kordylewski Clouds are doing something we don't expect? We often think of dust as passive, just drifting wherever gravity and radiation push it. But what if these clouds have dynamic behaviors we haven't detected yet? Could they shift and move in response to solar activity? Could they grow and shrink over time, fluctuating in ways we haven't noticed? One particularly intriguing idea is that these clouds might have an influence on Earth's own orbital stability. While the effects would be tiny, even small amounts of mass in the Lagrange points could create minuscule gravitational interactions with Earth and the Moon. Over millions of years, could these dust clouds have played a role in shaping the Moon's orbit or even Earth's long-term climate cycles? There's also the possibility that these dust clouds interact with cosmic rays and solar wind in ways we don't yet understand. The Kordylewski Clouds could be absorbing, reflecting, or even scattering particles from space, subtly influencing how energy moves through our region of the solar system. If that's the case, could they be contributing to unexplained variations in space weather, or even affecting how charged particles reach Earth's atmosphere? Some researchers have even speculated that the Kordylewski Clouds could help explain certain anomalies observed in Earth's upper atmosphere. For instance, strange fluctuations in atmospheric dust levels and unexplained variations in noctilucent clouds, those eerie, glowing clouds that form at the edge of space, could be linked to periodic interactions with the Kordylewski Clouds. If dust from these clouds occasionally drifts toward Earth, could it be subtly influencing atmospheric processes in ways we've never considered? The truth is, we don't know nearly enough about these mysterious clouds. Even with modern telescopes and space probes, they remain elusive, appearing faintly in polarizing light but largely invisible in normal observations. The next big step in solving this mystery will likely require dedicated spacecraft missions, probes designed to travel directly to the L4 and L5 points, collecting dust samples and mapping their structure in unprecedented detail. If we could send a mission to these clouds, what might we find? Could they be denser than expected? Could they contain unknown minerals or even exotic compounds that don't exist on Earth? And what if, hidden within these clouds, there are objects we haven't detected yet, small asteroids, frozen remnants of comets, or even artificial debris that has been trapped for decades? Perhaps most intriguingly, the Kordylewski Clouds challenge us to rethink what we consider empty space. We often imagine the space between planets as vast and empty, but in reality, it's filled with structures we are only beginning to discover. If massive dust clouds can exist right in our own cosmic backyard without being noticed for so long, what other hidden structures might be lurking elsewhere? Could there be similar dust clouds in the orbits of exoplanets, waiting to be detected? The more we learn about the universe, the more it surprises us. The Kordylewski Clouds are a perfect example of how even the most seemingly insignificant phenomena can open doors to entirely new realms of understanding. They might be just dust, but they could also be a key to unraveling deeper cosmic mysteries. And that leaves us with the biggest question of all. If these clouds have remained undetected for so long, what else are we missing? The Kordylewski Clouds remind us that our understanding of the cosmos is still full of blind spots. If something as large as these dust clouds can linger near Earth for decades without mainstream recognition, what else might be hidden in the shadows of our own celestial neighborhood? This question takes us to an even deeper mystery. Could there be other gravitationally stable points in our solar system that are also collecting dust, debris, or even larger objects? We tend to think of the Lagrange points as isolated, but in reality, they could be part of a larger system of gravitational pockets that act as cosmic storage zones. If so, then these dust clouds may not be unique. Similar structures might exist near other planets, or even in deep space, where they serve as temporary holding areas for interstellar material. If we could map all the hidden dust formations in our solar system, what would we find? Would we discover that every planet has its own version of the Kordylewski Clouds? Could these dust clouds be playing a role in shaping planetary atmospheres, influencing the movement of asteroids, or even providing a slow but constant supply of material for planetary rings? There's also a more unsettling possibility. What if these clouds occasionally release dust toward Earth in bursts that we haven't detected yet? It's possible that changes in the Moon's orbit, solar activity, or even the gravitational influence of passing asteroids could disturb the Kordylewski Clouds, sending waves of dust toward Earth's upper atmosphere. If this happens, could it explain sudden spikes in space dust levels, or even contribute to rare atmospheric phenomena that remain unexplained? We already know that Earth experiences periodic increases in micrometeorite activity, with dust grains constantly falling into our atmosphere. But could some of this dust be coming from a source much closer than deep space? If the Kordylewski Clouds are slowly shedding material, then some of it might be drifting toward Earth, influencing weather patterns or even long-term climate cycles in ways we don't yet understand. Another strange possibility is that these clouds might interact with Earth's magnetic field in unexpected ways. We tend to think of dust as inert, but in space, dust grains can become electrically charged. When exposed to solar radiation, they can develop tiny electrical charges that cause them to respond to magnetic forces. If the Kordylewski Clouds contain charged dust particles, could they be subtly interacting with Earth's magnetosphere? Could they influence the behavior of charged particles in near-Earth space, or even play a small role in shaping auroras and other magnetic phenomena? And then there's the question of what role the Kordylewski Clouds might play in long-term solar system evolution. Over millions of years, these dust clouds might not be as stable as we assume. Instead of being permanent structures, they could be shifting, changing, or even periodically disappearing and reforming. If that's the case, then they might be part of a much larger cycle, one that we're only just beginning to glimpse. One possibility is that these clouds could be tied to the Moon's own gravitational influence in ways we don't yet understand. The Moon is constantly tugging on Earth's atmosphere, creating ocean tides and even influencing the motion of Earth's crust. Could the Moon also be subtly shaping the structure of the Kordylewski Clouds, causing them to fluctuate in density over time? If so, then the presence or absence of these clouds might be linked to much larger cycles in the Earth-Moon system. Perhaps the most intriguing question of all is whether the Kordylewski Clouds might hold clues to the origins of our solar system. If these clouds contain ancient dust, material that has been trapped for billions of years, then they could serve as time capsules, preserving a record of the early solar system in a way that no other structure does. If we could analyze the dust within these clouds, what might we find? Would we discover that some of it dates back to the birth of the solar system, untouched for billions of years? Could we even find traces of material from beyond our solar system, grains of dust that originated in interstellar space and became trapped in Earth's gravitational influence? There's also the potential that these clouds might help us understand the movement of dust across the galaxy. We know that interstellar dust drifts between stars, but we don't fully understand how it moves or what causes it to clump together in certain regions. If the Kordylewski Clouds are interacting with interstellar dust in some way, then they might provide new insights into how dust travels between stars, forming the raw material for new planets and solar systems. Ultimately, the Kordylewski Clouds challenge us to rethink what we assume about our own cosmic neighborhood. They show us that even in a region of space we thought we knew well, there are still surprises waiting to be uncovered. And if we've overlooked something as large and persistent as these dust clouds, what else might we be missing? The mystery of the Kordylewski Clouds is far from solved. In fact, we may have only scratched the surface of what they really are and what they could teach us. As new technology emerges, we may finally be able to send dedicated probes to explore these hidden formations up close, revealing their secrets in ways we can only imagine today. But until then, one thing is certain: the more we study the universe, the more we realize how much we still don't know. And sometimes, the greatest mysteries aren't found in distant galaxies. They're right here, hiding in plain sight, just beyond the moon. The Kordylewski Clouds force us to reconsider a fundamental assumption: that we have already mapped and understood all the major structures near Earth. If something as massive as these dust clouds could remain hidden in plain sight for so long, then what other nearby phenomena might still be waiting to be discovered? It raises an unsettling but exciting question: what if space isn't as empty as we thought? This mystery leads to even bigger implications. Could other planets in our solar system have similar dust clouds? We already know that Lagrange points exist around all planetary systems, meaning that Jupiter, Mars, and even Venus might have their own versions of Kordylewski clouds. If these structures exist elsewhere, they might play an unseen role in planetary evolution. For instance, could Mars have a persistent dust cloud that affects its thin atmosphere? Could Venus have similar formations that influence its already extreme weather? And then there's the idea that these clouds could be more dynamic than we think. What if they aren't permanent structures but instead form and dissipate over time? If that's the case, then the Kordylewski clouds might be part of a much larger, ongoing process, one that involves dust movement on an interplanetary scale. Some scientists speculate that cosmic dust could play a role in seeding planets with the building blocks of life. Could these clouds be acting as collectors, gathering dust from deep space and occasionally releasing it toward Earth? The question of their composition is another mystery. What exactly is inside the Kordylewski clouds? Are they made up of purely lunar dust that has escaped from the moon's surface, or do they contain material from deeper space? If we could take a closer look, we might find that these clouds hold remnants of ancient asteroid collisions, particles from passing comets, or even interstellar grains that have drifted into our solar system. One of the strangest possibilities is that the Kordylewski clouds might act as cosmic filters, capturing material that enters Earth's gravitational sphere and holding onto it before eventually releasing it. If so, then these clouds could contain a mixture of matter from multiple sources, some from the moon, some from deep space, and some from unknown origins. The study of these particles could offer a new way to examine the chemical history of our solar system. This raises another important question: have the Kordylewski clouds always been there, or did they form relatively recently? If they are ancient, they might be leftover debris from the early days of the Earth-Moon system, dating back billions of years. But if they formed more recently, we have to ask, what event caused them to appear? Could they be the result of a past asteroid impact on the Moon? A disturbance caused by changes in Earth's orbit? Or could they be temporary structures, forming and dissolving depending on solar and lunar conditions? Another major mystery is their interaction with the solar wind. We know that the Sun constantly emits charged particles that travel through space at incredible speeds. These particles, known as the solar wind, can push dust and alter its movement. If the Kordylewski clouds are exposed to these forces, then they might not be as stable as we think. The solar wind could be shaping them, shifting their location, or even breaking them apart and reforming them over time. If these clouds do shift, it could explain why they have been so difficult to detect consistently. They might not always be in the same place, or they could change density based on solar activity. During periods of high solar radiation, the clouds might thin out, becoming nearly invisible. During quieter periods, they might grow denser, reflecting more light and becoming easier to observe. This could explain why past studies have struggled to confirm their existence with certainty. The more we learn about these dust clouds, the more they seem to be connected to other space phenomena. Some researchers have even speculated that the Kordylewski clouds could interact with Earth's atmosphere in subtle ways, affecting things like cloud formation or high-altitude weather patterns. If small particles from these clouds slowly drift toward Earth, could they influence the chemistry of the upper atmosphere? Could they contribute to noctilucent clouds, those eerie glowing clouds that sometimes appear high above the poles? Another possibility is that the Kordylewski clouds could act as a barrier against incoming cosmic radiation. Space is filled with high-energy particles that constantly bombard Earth. But what if these dust clouds help absorb some of that radiation? If they contain electrically charged particles, they might interact with cosmic rays, altering their paths or slowing them down. This could have implications for understanding how radiation affects astronauts, satellites, and even Earth's climate. And then there's the biggest question of all: what else might be hiding in the shadows of our solar system? If the Kordylewski clouds managed to avoid detection for so long, could there be other unknown objects or structures lurking in gravitationally stable points? Some scientists have even proposed that small, undiscovered moons or asteroids could exist in these locations, hidden by the very dust that makes up the clouds. If that's true, then the Kordylewski clouds might not just be floating dust. They could be part of a much larger system of hidden celestial objects. Could there be tiny, dark asteroids within these clouds, acting as gravitational anchors? Could these dust clouds be hiding something even stranger, objects that don't fit into our current understanding of planetary science? The only way to find out is through direct observation. While ground-based telescopes have struggled to capture the Kordylewski clouds clearly, future space missions might be able to investigate them up close. A spacecraft equipped with dust collectors, high-resolution cameras, and radiation sensors could fly through these clouds and analyze their composition directly. Such a mission could answer some of our biggest questions. Are these clouds stable, or are they constantly changing? What kind of material do they contain? How do they interact with Earth, the Moon, and the solar wind? And perhaps most intriguingly, what else might be lurking within them? The Kordylewski clouds remind us that the space near Earth is still full of surprises. For centuries, we've assumed that the region between Earth and the Moon was empty, a vast nothingness between two celestial bodies. But now, we know that this isn't entirely true. Something is there, something large enough to be detected, yet elusive enough to have remained hidden for decades. This discovery changes how we think about space. It forces us to reconsider what else might be hiding in plain sight, waiting for us to take a closer look. If we've missed something as significant as the Kordylewski clouds, then what other cosmic secrets are still out there, waiting to be uncovered? The universe is full of mysteries, and sometimes, the biggest ones aren't in distant galaxies or black holes billions of light years away. Sometimes, they're right next to us, floating just beyond the Moon, waiting for someone to finally pay attention. The presence of the Kordylewski clouds challenges the way we perceive the immediate space around Earth. These massive dust formations, hidden in gravitationally stable zones, make us question what other unseen structures might exist in our cosmic neighborhood. If such a phenomenon could remain undetected for so long, how many other celestial structures have yet to be found? Could there be other dust clouds, unknown natural satellites, or even faint planetary rings orbiting Earth or other planets in our solar system? One of the most fascinating aspects of the Kordylewski clouds is their connection to Lagrange points, specific locations where gravitational forces balance in such a way that objects can remain relatively stationary. These points exist not only in the Earth-Moon system but also between all major celestial bodies. The fact that these clouds persist in Earth's L4 and L5 points suggests that similar dust formations might exist around other planets, including Mars, Jupiter, and even exoplanets in distant solar systems. If we find similar dust clouds elsewhere, it would indicate that this is not just an anomaly but a natural phenomenon occurring throughout the cosmos. The implications of this are profound. If these dust clouds exist around other planets, they could affect everything from planetary weather patterns to the way we detect exoplanets. When astronomers search for planets beyond our solar system, they often look for how these planets block starlight or reflect light from their host stars. But what if some of the light variations we observe are caused by massive dust clouds rather than the planets themselves? Could some of the strange light fluctuations seen in distant solar systems actually be caused by Kordylewski-like clouds rather than planets or alien megastructures, as some have speculated? But let's turn our focus back to the Earth-Moon system. What role, if any, do the Kordylewski clouds play in the long-term evolution of our planet? Some researchers speculate that these clouds might serve as a kind of cosmic buffer, absorbing some of the interstellar material that enters our region of space. If so, they might act as a collection zone for extraterrestrial particles, potentially including materials from beyond our solar system. By studying the dust in these clouds, we might uncover microscopic fragments of ancient asteroids, comet tails, or even interstellar matter that drifted into our solar system from another star. One theory suggests that these clouds might even act as temporary holding zones for space debris and micrometeoroids. As these tiny particles become trapped in the Lagrange points, they might slowly spiral inward toward Earth, eventually entering our atmosphere. If this is happening, it could mean that the Kordylewski Clouds contribute to periodic meteor showers or unexplained bursts of incoming cosmic dust. Some meteor showers are well understood and linked to cometary debris, but others remain mysterious. Could these clouds be a hidden source of some of the unexplained space debris that occasionally rains down on our planet? Another strange possibility is that these clouds might play a role in space weather. Space weather refers to the conditions in space that affect Earth's atmosphere, including solar wind, cosmic rays, and geomagnetic storms. If the Kordylewski clouds interact with solar radiation, they might contribute to fluctuations in Earth's magnetic field. This, in turn, could influence everything from satellite operations to radio communications and even auroras in the polar regions. If dust in these clouds becomes electrically charged, it could create subtle electromagnetic effects that we have yet to understand. And what about the Moon? Given that these clouds exist in the Earth-Moon system, could they have any impact on the lunar surface? If these dust clouds occasionally shift or lose material, then small amounts of this dust might end up settling on the Moon over time. If that's the case, then lunar dust samples might contain traces of Kordylewski cloud particles, offering a way to study them indirectly. Future Moon missions, including those planned by NASA and private space companies, could analyze lunar dust for evidence of these mysterious clouds. Despite all these possibilities, the Kordylewski clouds remain incredibly difficult to observe. Unlike planets, moons, or even asteroid belts, they don't emit their own light or strongly reflect sunlight in a way that makes them easily visible. Instead, they are faint and diffuse, blending into the background of space. This makes them almost like ghosts, present but nearly impossible to see. The best evidence for their existence comes from polarization studies, which analyze how light interacts with dust particles. The 2018 study that confirmed their presence relied on detecting polarized light reflected from the dust, but even this method is challenging. The signal from these clouds is weak, and it's difficult to separate from other sources of scattered light in space. This raises an intriguing question. If the Kordylewski clouds are so faint, could there be even more of them that we haven't detected yet? Could there be smaller dust clouds hidden in other Lagrange points or floating elsewhere in the Earth-Moon system? If we could get a spacecraft close enough to these clouds, we could directly measure their density, composition, and structure. A mission to the Kordylewski clouds would not only solve many of these mysteries but might also reveal entirely new aspects of space near Earth. Scientists could analyze whether these clouds contain purely lunar dust or if they have accumulated material from deeper space. They could also determine whether the clouds are stable over long periods, or if they change in response to solar activity. Beyond scientific curiosity, understanding these clouds could have practical applications. If future space missions travel through Lagrange points, knowing the density and behavior of these dust clouds would be crucial. Spacecraft passing through these regions might experience unexpected dust accumulation or interference from charged particles in the clouds. By studying them now, we could better prepare for future lunar exploration, deep space missions, and even potential space habitats in these regions. As our ability to explore space improves, the Kordylewski clouds serve as a reminder that the universe still holds secrets, even in places we thought we had fully mapped. The more we study them, the more questions arise. What other hidden structures might exist in our solar system? Are there other gravitationally stable zones harboring unknown clouds, asteroids, or even mini-moons? And if these clouds have been around for billions of years, what role have they played in Earth's history? Have they influenced meteor showers, atmospheric chemistry, or even the conditions that allowed life to thrive on our planet? Could they have been part of a long-forgotten cycle of dust exchange between Earth and the Moon? The Kordylewski Clouds remind us that space is far more complex than it appears. Even in the regions closest to Earth, where we assume we have discovered everything, new mysteries continue to emerge. And if something as large as these clouds could remain hidden for so long, it makes you wonder, what else is lurking out there, just beyond the reach of our current understanding? The Kordylewski Clouds raise another fascinating question. How do they interact with Earth's natural environment over long periods? If these clouds are stable and have existed for millions, or even billions, of years, then they might have played an unseen role in shaping our planet's space environment. Some scientists suggest that Earth's upper atmosphere might be subtly influenced by these dust clouds, particularly in ways we don't yet understand. If these clouds slowly deposit microscopic dust particles into Earth's atmosphere, they could contribute to the thin layer of cosmic dust that constantly falls to our planet. Each year, Earth accumulates tons of cosmic dust from meteors, comets, and interstellar debris. Most of this dust burns up in the atmosphere, creating what we see as shooting stars. But some of it reaches the surface and becomes part of Earth's geological record. Could the Kordylewski Clouds be a long-term source of this cosmic material? If so, then traces of their dust might be locked inside deep-sea sediments, ice cores, or even ancient rock formations. Analyzing these materials could offer clues about how long the clouds have been present, and whether they have changed over time. The idea that Earth is constantly interacting with unseen cosmic structures isn't new. Scientists already know that the Sun moves through regions of interstellar dust as it orbits the Milky Way, and that Earth's position within the galaxy can influence everything from climate patterns to the frequency of asteroid impacts. But what if smaller-scale interactions, like those involving the Kordylewski Clouds, also have long-term consequences? Could tiny shifts in the density of these clouds subtly alter the amount of solar radiation that reaches Earth? Could they contribute, in some small way, to climate fluctuations over long periods? Another potential effect of these clouds involves their interaction with Earth's magnetosphere. The magnetosphere is a protective bubble of charged particles that shields our planet from solar wind and cosmic radiation. If the Kordylewski Clouds contain electrically charged dust, they might interact with this magnetic field in ways that haven't yet been studied. This could create faint but measurable disturbances in the way Earth's magnetosphere behaves, potentially affecting space weather and even satellite communications. Speaking of satellites, the presence of the Kordylewski Clouds raises concerns for future space exploration and technological infrastructure. As humanity continues to expand its presence in space, through satellites, space stations, and potential lunar bases, understanding the exact nature of these dust clouds becomes more important. While the dust in these clouds is sparse, it still poses a potential risk to spacecraft passing through L4 and L5. Even tiny particles traveling at high speeds can cause damage to sensitive instruments, solar panels, and communication systems. If future space missions plan to use Lagrange points for long-term operations, scientists will need to account for the presence of these clouds. Space agencies like NASA, ESA, and private space companies might need to develop shielding methods to protect spacecraft from dust accumulation. This could be particularly important for missions involving lunar exploration, as some proposed lunar space stations are expected to operate near these Lagrange points. Another intriguing possibility is that the Kordylewski Clouds might not be entirely natural. While current evidence suggests they are composed of naturally occurring dust, it's worth considering whether other processes could contribute to their formation. Could human activity in space, such as rocket launches, satellite debris, or even lunar dust kicked up by past missions, play a role in shaping these clouds? If the dust composition of these clouds is ever found to include unexpected materials, it could hint at a more complex origin than previously thought. Beyond our own planet, studying the Kordylewski Clouds might provide insights into similar dust clouds that could exist elsewhere in the solar system. If stable dust clouds can form around Earth, then they could also form around other planets with moons, such as Mars, Jupiter, and Saturn. This raises the possibility that hidden dust formations exist throughout the solar system, waiting to be discovered. Jupiter, for example, has an extensive system of moons, and its gravitational environment is even more complex than Earth's. Could there be undiscovered dust clouds in Jupiter's Lagrange points, influenced by the planet's immense gravitational pull? And if similar clouds exist around Mars, they could impact future missions and colonization efforts. Even beyond our solar system, Kordylewski-like clouds might exist in the orbits of exoplanets. If these dust clouds are a common feature of planetary moon systems, then astronomers searching for exoplanets might need to account for their presence when interpreting light signals from distant star systems. Some unexplained variations in starlight, which are currently attributed to exoplanetary atmospheres or asteroid belts, might actually be caused by similar dust clouds. Ultimately, the study of the Kordylewski clouds represents an ongoing mystery, one that reminds us just how little we truly know about our own cosmic backyard. Even though we've mapped most of the large celestial objects in our solar system, there are still structures hiding in plain sight, waiting to be uncovered. If something as large as the Kordylewski clouds could remain undetected for so long, it makes you wonder, what else is out there, just beyond the reach of our telescopes and satellites? This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.